From 1946 through 51, the Fairchild Airplane Company conducted feasibility studies for nuclear propulsion for aircraft, or NEPA. Various cycles, power plants, and nuclear reactors were explored. Among the decisions was that the jet engine, still in its infancy, was to be used. In 1951, a decision was made that GE-A&P was to develop the direct cycle concept where the air from the compressor was heated directly by the reactor fuel elements. Major elements of the A&P program are shown on the chart. During the 1951 to 53 early nuclear flight was an objective to determine operational feasibility of a nuclear-powered aircraft. The test aircraft was to be a B-36. The power plant consisted of 4 modified J-47s designated the X-39. The energy was supplied by one R-1 reactor. The R-1 was water moderated and had an aluminum structure. The fuel element consisted of a 310 stainless steel plus UO2 matrix, which was clad with stainless steel. The program was redirected in early 1953. 3 heat transfer reactor experiments, heaters, followed. From 1952 through 61, the divided shield design was validated and various shield materials were tested in the Tower Shield facility at Oak Ridge. Also, 40 test flights of a B-36 with a small 2 megawatt thermal reactor aboard were conducted by Convair at Fort Worth. On January 31st of 1956, in the Heater 1, the first jet engine operated on nuclear power at the National Reactor Test Station in Idaho. The fuel material was nichrome plus UO2. Tests began in 1957 of the Heater 2. It was similar in design to the Heater 1, but with an 11-inch hole in the center of the core, where advanced fuel element and moderator designs were tested until 1961. The Heater 3 was built in a full-scale aircraft reactor configuration. It was tested using an air-cooled solid moderator, zirconium hydride, and nichrome were the fuel elements. 2 X-39 engines were operated at full power. Nuclear starts were demonstrated. From 1956 through 59, the XMA-1A development program was to meet the Air Force Camel mission, including supersonic sprint. New twin X211 engines shared a reactor between them. A new solid moderator of yttrium hydride with capability of 2300 degrees Fahrenheit was developed. However, the advanced fuel element, though structurally improved, did not yet have the capability of 1800 degrees Fahrenheit turbine inlet temperature. By 1959, development tests demonstrated that a BEO ceramic reactor would meet the 1800 degree Fahrenheit turbine inlet temperature. The XNJ-140 power plant had one X211 engine with a ceramic reactor. It provided 100 megawatts at cruise conditions. By March 1961, other competitive weapons systems, such as missiles and nuclear submarines, had obviated the need for a nuclear-powered aircraft. Therefore, the A&P program was canceled. This is a model of a nuclear-powered jet engine, the XNJ-140. It is 1/10 scale. The actual engine was 37 feet in length. This is the compressor, the reactor with the shield assembly, the combustor, the turbine, and the nozzle. By the end of 1960, 11 builds of the turbine machinery did operate in Cincinnati on chemical fuel. The XNJ-140 was scheduled to operate on nuclear power in 1962 at the National Reactor Test Station in Idaho. This is a model of the Convair NX-2 aircraft. It was to fly in 1965. The canard configuration is well suited for a nuclear-powered aircraft. There are 3 Exxon J140 engines at the rear of the fuselage where they're accessible for the remote handling and maintenance. 100 feet forward is the crew compartment, which is shielded. Air inlets to the engines are located at the base of the wings. J-75s are mounted in pods and are used for takeoff only in the event of a loss of an engine. The hangar to house this aircraft and provide the remote maintenance was constructed in Idaho by April of 1961 when the Aircraft Nuclear Propulsion program was canceled. 1945, the temperature reached 108 degrees in the afternoon at Mindanao. But lo and behold, we were issued new rifles, OD winter clothes, and OD blankets, as well as other equipment. Rumors were flying that the Japanese islands were next. Meanwhile, on the 6th of August, several people were loading the bomb into the Enola Gay's bomb bay. One of these men was Gunnar Thornton. Gunnar, whom we have with us, fortunately, today, will you describe that short film?
First, a minor correction. It was on the 5th of August because the bomber took off bright and early in the morning on the 6th of August, and everything had to be ready, naturally, on the 5th. So basically, I was a member of the Los Alamos group out there, the so-called Project Alberta, which consisted of about 50 people from Los Alamos, which was a mixture of civilians and naval personnel and military personnel of different ranks and responsibilities. Generally, it was not a militaristic type of operation, and that Oppenheimer had insisted that this simply be a technical group. The Project Alberta bunch was the one that actually brought the bomb to their responsibility was to deliver the bomb to the Air Force, which was represented by the 509th group, of which Tibbets was the commander. So the little piece of film that you saw was after we'd taken the bomb out of the assembled bomb out of the Quonset hut where we had done the assembly work and opened the rear doors to the backyard there, which was a backyard. This was actually the gun bomb to be used on Hiroshima. This backyard was shared then by another Quonset hut which had the Nagasaki bomb, the implosion bomb. So what you see is the bomb was wheeled out And I think at that point we had it covered over with a piece of canvas. And so the guy in kind of ragged clothes, which we were apt to have at the time, that kind of said or acted like get the show on the road and pushed the rear end of the bomb around and started shoving it towards the gun carriage. That was me. So from then on, I jumped on board the gun carriage, rode up to the loading pit, and generally once we got it to the loading pit and in position, we handed it at that point over to the Air Force for most of the work.
What were some of the events that led up to the atomic airplane?
Well, let's see. We could go back, extremely ancient history, but maybe what we ought to do is go back to a book that was written by H.G. Wells. And let's see. H.G. Wells in the year 1914 put out a book called The World Set Free. Now, this is a book in which he predicted the development of the atomic bomb. And he had done this mostly on the basis of conversations with a physicist or chemist, Soddy, S-O-D-D-Y, who was a contemporary of the Curies. And he went into quite a bit of detail then about the story about the development of an atomic bomb. And Leo Szilard, who was the guy that got Einstein to write the famous letter to Roosevelt, which kicked off the atom bomb program, he had read this book. And I really didn't know of its existence at the time. And much later, in the 1930s, there was a lot of talk about atom bombs. People didn't know how to release the energy yet, but there was a lot of talk about it. But Wells was talking even in 1914. Well, although nothing was said, at the time, he not only talked about atom bombs, he talked about atomic airplanes. Now, if you'll give me that book, I'll show you, I'll maybe read you a passage or two about what he said about atomic airplanes and atomic locomotives and atomic automobiles and all kinds of...
Atomic roller skates?
Well, we haven't quite got to the single-bladed roller skates yet, but let's see now. Okay, in fact, in talking about atomic airplanes, for example, he says here the new atomic airplane, bear in mind this was 1914, the new atomic airplane became indeed a mania. Everyone of means was frantic to possess a thing so controllable, so secure, so free from the dust and danger of the road. And in France alone, in the year 1943, Wells predicts, 30,000 of these new atomic airplanes were manufactured and licensed and soared humming softly into the sky. And with an equal speed, atomic engines of various types invaded industrialism. The railways paid enormous premiums for priority in the delivery of atomic traction engines. Atomic smelting was embarked upon so eagerly as to lead to a number of disastrous explosions due to inexperienced handling of the new power. And the revolutionary cheapening of both materials and electricity made the entire reconstruction of domestic buildings a matter merely dependent on reorganization of methods, etc., etc. So he does a lot of talking about things here, and the idea was that there was so much more energy in this atomic thing. The one thing that he's off by rather grossly is he figured that a ton of uranium was equal in energy. Let's see here now what he says. Okay, no, it was even less than that. He had a bottle of a pint of uranium oxide, and he figured that was equal in energy to 160 tons of coal. Now, if you work that out, he was really underestimating. The real ratio is a pound of uranium-235 has, if you could release it, has the energy of about approximately 2 million pounds of coal. So you have a multiplication of about a factor of 2 million. And that, incidentally, is one reason why the weight of the waste from the atomic energy is so low, because of the fact that there's a proportionate small amount of waste. And that's one reason why it's so silly that people are so worried about this, and why we can store the waste around on the sites. There was so little of it that from an engineering viewpoint, it isn't a massive problem. Not only that, but the waste from coal gets multiplied because you burn oxygen from the air that adds in the combustion products to the mass of waste. So the waste problem is really from conventional fuels is much worse than it is from nuclear, but you have to be careful nevertheless. So the thing, though, that he gets at here is everybody had their atomic airplanes and their atomic bombs, and they got to flying around and dropping bombs on each other's factories and countries and all that kind of stuff. And things kind of got out of control. And so after a while, the various countries in the world thought, gosh, we just can't let this keep going like this. We better settle down and get this thing stabilized. And so they did. And the net result of the development of the bomb in particular, but to some extent the nuclear airplane, but especially nuclear power and so forth, had the effect of stabilizing the world. That's why they say that the world set free. And what Wells says in here is that this would have happened eventually anyhow, because we would have kept fighting with conventional weapons, and there would have been more people, and it would have become intolerable that the world continue this way. But the advent of the atomic bomb accelerated by several centuries the point at which the world, people in the world realized that it was intolerable to just simply continue having wars. So he says that was the big contribution. And when you think about it, that may be, in fact, probably is exactly what happened, the fact that these bombs were used. We mentioned before already that Mr. Wells, H.G. Wells, wrote a book about, in which he mentioned nuclear aircraft and so forth. At the time, people knew there was energy locked up because they could tell from measurement of the energy of the particles that were released from uranium and so forth that there had to be a lot more energy available that far exceeded the kinetic energy from combustion or chemical processes. You'd measure an alpha particle that had a huge amount of energy compared with some combustion product or chemical reaction product. So people did a lot of speculating. Wells did, and then afterwards it got to be very popular in the 1930s to speculate about nuclear airplanes, about nuclear ships, and so forth. And I was very much interested in all that kind of stuff. And I followed those things, but other people were also. Mm-hmm. And it started to appear in the newspaper. Newsweek magazine had started to give progress reports on the German atomic energy program back in the early 1940s. And those reports stopped at some time, but there were several issues in which they were saying something about that. So during the war then, there were people that speculated about it. And in particular, in the NEPA final report, which came out in, 1951, and this was, NEPA 1830 or 1630, it goes into specifically the event, the key event, and mentions the fact that people had speculated during the war. Some people who had gotten things like the K-25 plant going were still on the payroll. They were making the plant work better, but they had a little more time on their hands, and they were able to start speculating. Some of the speculations involved not just the bomb work, but the power-producing reactors, nuclear airplanes, nuclear ships, and so forth. And in particular, there was a guy that worked for J.A. Jones Construction, And let me just read a little bit out of the NEPA final report.
All right.
Here it says, in industry, 2 men were responsible to a large measure for the birth of the NEPA project. And again, let me remind you, NEPA, nuclear energy for the propulsion of aircraft. These men were J. Carlton Ward, Jr., then president of the Fairchild Engine and Airplane Corporation, and Gordon Simmons, a young mechanical engineer then in the employ of the J.A. Jones Construction Company, the construction company which erected the large K-25 gaseous diffusion plant at Oak Ridge. So Simmons then obviously had an insight. He was an insider as far as the Manhattan Project was concerned. And he probably knew a lot more about the bomb and a bunch of other things than people generally think, because generally people working on the project weren't as ignorant of everything else. You hear these stories that they were compartmentalized and didn't know anything about what the other guys were working on. That was true. That was true to some extent, but the point is people kept their mouths shut. Mm-hmm. And I'm sure that Simmons knew a great deal. He probably, towards the end, had more time on his hands because the K-25 plant was running and needed fixing and so forth. And it's not out of the question that I just don't know what, if any, part Fairchild had played in the Manhattan Project. But I would not be at all surprised if at some point in time that J. Carlton Ward, president of Fairchild, and Gordon Simmons had some conversations, bootleg or otherwise. Fairchild was known as working on leading edge stuff. They always had, there was always at the front end of the innovative ideas as far as aircraft were concerned. So Simmons had these ideas about making this nuclear airplane. So here's the key sentence, the very event. Simmons' thoughts were stimulated, wait a minute, Ward, it said, had been thinking about this, but it says that J. Carlton Ward's thoughts were stimulated by a letter dated 27 August 1945, which Gordon Simmons addressed to Sherman Fairchild, then chairman of the board of Fairchild Engine and Airplane Corporation, in which Mr. Simmons stated that he would like to be connected with a company that would be interested in applying nuclear energy to the propulsion of aircraft. Okay, so if you can say there's any point at which it started in the form of a piece of paper, it was that letter.
That would be that letter.
On August 27th, 1945. And I might point out that that was only 10 days after the end of the war with Japan. So it is very likely that Gordon Simmons had composed this letter well ahead of time, but had waited until he could legally say something. Well, okay. As a result, a conference was held in the Fairchild, New York office in October 1945, attended by Simmons and others, at which it was decided that the Fairchild company was definitely interested in the sponsorship of such a project and would make representations to the military services to that effect. Now, I'll read a little more here because it again brings in characters. After subsequent conferences and further studies, consultation with Major General L.R. Groves, Brigadier General Nichols of the Manhattan District, Rear Admiral Stevens of the Bureau of Aeronautics, and after evaluation of other proposals received from other companies, such as Northrop, the Kellex Corporation, the Gabriel Giannini Company, Army Air Forces, then part of the War Department, decided to sponsor a single unified project under the management of one industrial company, with which all the companies in the recognized aircraft engine industry would be invited to participate. It was also considered desirable for the National Advisory Committee for Aeronautics to participate on par with the aircraft engine industry in this thing. So a meeting then was held at the Pentagon. Bear in mind this is now early fall of 1946, in which all interested agencies and companies were represented. Lieutenant General Curtis LeMay and Major General Crawford outlined the various consideration and the Air Force views on the subject. And discussion brought forth unanimous concurrence of all participants that this thing ought to be looked into. Whereupon, now the Air Force did a very strange thing. Whereupon the Air Force asked the industry members to select one of their companies as the single manager of the group effort and as the recipient of an Air Force prime contract. After the military representatives had excused themselves temporarily from the conference, the meeting was continued under the chairmanship of Burdett Wright, then president of the Curtiss Wright Corporation. And 1 hour later, it was announced that the Fairchild Company had been unanimously selected as the leader and single manager of the aircraft engine industry group effort. Now imagine that.
That's pretty doggone fast, isn't it?
The military walking out and saying, you guys decide. These guys talk for an hour, and they decide that Fairchild should do it, and the reason they did was because Carlton Ward and Simmons had taken the lead in the thing, and they'd done more thinking. These other guys, they were going to be involved. They were part of the act, but you know, somebody else could get things going. So, you know, that is an amazing thing. Thus, the NEPA project began officially on May 28, 1946, with the signing by General Spaatz of an Air Force letter of intent, co-signed by Major General Groves. Associated with Fairchild in the capacity of member companies were Allison Division General Motors, United Aircraft Corporation, Wright Aeronautical Corporation, General Electric Company, Westinghouse Company, Continental Aviation and Engineering, Lycoming Division of the Avco Manufacturing Company, Frederick Flater Incorporated, Northrop Aircraft, and Manasco Manufacturing Company. So that is how the thing was kicked off. Okay, so Fairchild started these studies. They gathered together people that they could, and of course there were a lot of very capable people that had worked on engines of various types. You know, this was, you know, the war was over. We'd used engines during the war, including both reciprocating engines and early turbojet engines. Turned out the gas turbine engines, and looking at patent work later on, had a much more ancient history than I had thought. We had a guy come in with some ideas, and checking back on the patents, we found out a lot of the patents issued, basic patents on gas turbines, were issued to this, who was it? Was it Rateau? I think it was Rateau back in the 1890s. It was very hard to find any basic thing that hadn't already been patented in the 1890s. But the early conclusions, and they got some very, very capable people in there, and generally advanced thinkers, you might say, but people who had actually worked on real engines and real airplanes during and before the war. So the early conclusion there in their first report, the first NEPA report in 1946, they said, in general, it appears that nuclear power can be used as a source of thermal energy for all basic types of power plants, including closed-cycle condensing turbine, that means steam turbines. And steam turbines were actually looked at very seriously. Mm-hmm. Steam turbine has a huge advantage in that it's the so-called Rankine condensing cycle. And you can move from steam to condense it into water, which is easy to pipe around, and then you reheat it. And it's, Rankine cycle is a great cycle, and that's what we use in central station power plants. Closed cycle gas turbine, open cycle turbine, turbojet, ramjet, rocket. The range of practical applications and the usefulness in relation to chemical energy engines will depend primarily on the temperature at which the nuclear reactor can be operated. And that again, of course, then put the problem right on the into the lap of the materials people. Now, thing is that in a gas turbine engine or in an automobile engine, the working fluid, the products of combustion, operate at run at a much higher temperature than the structural temperature. The structure is cooled in those things, but the working fluid runs at high temperature, and the walls, which might melt or corrode, only see the radiation from those things. By being very clever, we protect the walls from damage. Take the ordinary automobile engine. That combustion takes place at, 4,000, maybe even 5,000 degrees. There's a little explosion.
But it depends upon the oxygen
Yeah.
compression.
Well, the material can't stand that temperature. But, it's reciprocating and for a bunch of reasons, and we're cooling the walls with water and so forth. But in the nuclear reactor, you have to have the uranium inside a fuel element of some kind. And the heat then that is being produced in there has to go through a material. So in order to use it to heat some working fluid, you have to have that material withstand the temperature. And so consequently, you're limited then by the transfer, the so-called heat transfer nuclear reactor. You are limited by the temperature of the metallic materials or ceramic materials to an extent much greater than is the case in other engines. Now, we can't get into that in great detail right now. But let us pause just for a minute and say, okay, where does this energy come from? Well, we know where it comes from in an ordinary turbojet engine or in our automobile engine. We burn some fuel in the presence of oxygen, and we heat the air, which is actually primarily nitrogen. So really, we're heating air, and we're pushing a cylinder, or we're pushing a turbine with hot air. We've got some energy still in the thing, and we put out an exhaust that has a velocity which pushes the airplane along, or we drive a fan from our little engine here, and the fan is kind of like a big, huge ducted propeller. And so that the turbine, or a turbojet, the jet, is really hot air. That's what's pushing us, and really it's hot nitrogen mostly, because air is mostly nitrogen. So really all we have to do in the nuclear engine is heat the air somehow or other, which we're going to do, as I said, by getting hot fuel elements. Well, there were people that didn't believe that. Members of the academic community. They thought somehow you had to have impinge on the blades, high velocity products, fission products, and they believed that in ordinary jet engines you were impinging combustion products on the blade, and that was what was turning the engine, the turbine. They didn't believe that it was hot gases. Now, I've told that to people, and they can't believe that what I say is true, but believe me, there were people, and I could mention some very prominent physicists who just were not convinced that you could run an engine off of hot air. It is hard to believe that, and it's hard for people to accept that when I tell them. And so we even had to go to the point, and this was happening at Fairchild just when I got there in 1948. They had to take a small turbine engine and take electrical heating elements and put it in place, the electric heating elements in place of where the combustor was on the turbine. And the air came out of the compressor, and it was heated by going over these electrical heating elements, and it drove the turbine. And lo and behold, it worked. The turbine rotated the compressor. There was extra energy that came out the back in the form of a jet, so that disposed of that problem. But, it is hard in retrospect to think that that is one of the hurdles that had to be overcome. These studies went along, and by 1948, when the NEPA project was 2 years old, the AEC started to get interested in the thing. And it had been sponsored up until that time by the Air Force, and they established the so-called Lexington Project study, which was a study with MIT. And they got then some very well-known and capable academic people with representatives from industry also to study this, and so they did, and they said that they feel that it is feasible. Now, but let's see how they put it here now. AEC, okay, Lexington. In its report, dated September 30, 1948, the Lexington Project concluded that although success cannot be guaranteed, there is a strong probability that some version of nuclear-powered flight can be achieved if adequate resources and competent manpower are put into the development. The aircraft would have a speed approaching the velocity of sound, probably 600 miles per hour, at an operating altitude of at least 30,000 feet, but probably not much over 50,000 feet. A manned nuclear powered plane would be very large, perhaps larger than anything yet constructed. And that was true. When the program ended, we were on a 600,000-pound airplane, but you bear in mind that the big transport now, like the the commercial transports, are way up to 800,000.
Yeah, true.
So, as the planes got bigger, it got more feasible to have these things. They said a tug-tow combination currently appears to be the most promising project. Well, that tug-tow was dropped out because somebody had their time machine, and they'd been reading about this satellite that they tried to put out on this reel in 1996, and lo and behold, the tow rope broke, and they lost the satellite. So somebody had probably H.G. Wells had that in his book. So somebody ruled out the tug-tow. So then the key thing in the Lexington report, the project recommended that if it is decided that as a national policy, the high cost and technical manpower, fissionable material, and money can be justified, a strong development program on nuclear-powered flight should be undertaken. And that was indeed done. This recommendation was accepted. And in February of 1949, then, it was decided that the nuclear-powered program would become a joint effort of the Air Force, the Navy, AEC, and NACA. And so that was in 49, and it was at about that time then that the AEC felt that they better get people into the program that they were familiar with and recognized, and one such person now, with the cast of characters increasing, was Miles Leverett. He was a man with a lot of experience in the Manhattan Project, well respected by the Atomic Energy Commission and so forth, and they probably couldn't have picked a better representative to come in and represent that knowledge and so forth coming out of the AEC-sponsored programs. Well, what Fairchild did then, or on the NEPA project, they studied these various things and came up then with the early conclusion that the most likely ultimate successful candidate would be a reactor, a ceramic reactor consisting of a mosaic of fuel elements, or a bundle of, maybe beryllium oxide or things that we did indeed end up in GE working on. And Fairchild started then development on those things to make hot air to drive a turbojet and so forth. But they also point out that there are all kinds of problems in these ceramic reactors. You've got to hold together this big bundle of things, and later speakers will talk about some of those problems and how they were encountered later on in the GE program. Well, shortly then, these were indeed big problems, the thermal expansion problems and so forth. But then what happened is there was an invention made, and there's a patent out on it held by Walter Thompson and Austin Corbin, in which they used a water-moderated reactor. The water served to cool the reactor structure and to moderate the neutrons. Moderating the neutrons is the neutrons bounce around, hitting the hydrogen in the water. They get down to an energy where they're more easily absorbed by the uranium. And then using metallic fuel elements. The metallic fuel elements are to a considerable extent modeled after the metallic fuel elements used by the Navy in the Navy submarine program and used in these so-called swimming pool reactors. A sandwich in which you had some outer material and then inside two layers of a metal, which could be, in the naval reactors, could be zirconium or aluminum, because they're relatively low temperatures, and then the inner meat of the sandwich consisting of the same material mixed with uranium oxide. So here was a way of getting away from the structural problems, but still make a reactor in which you could gain a lot of experience with nuclear and so forth. And at first, the idea was to make slabs of water, cans of water in the form of slabs, and then fuel elements in between these things. Later, it was made into big concentric rings in diameter, annular rings of water held by aluminum. And then there were to be stainless steel or nichrome fuel elements impregnated with uranium oxide in between. That was the original concept. That was all done then up to that point under the Fairchild project. And whereas when the project then, it was decided then in late, with this development and seeing a way that you could get into early development and get something started without really going to the ultimate, it was decided that it was now a time to get beyond the study phase and get an industrial contractor in there. And as Fairchild themselves had recommended, give it to one contractor. And General Electric was selected then, and they took over then the NEPA project work. And they soon after that, but it was decided in their early studies that they would concentrate on the GE would on the air-cooled direct cycle reactor. Pratt & Whitney was brought in to work on a reactor in which you heated liquid sodium in the reactor off to the side, and then you piped it into a heat exchanger and used that heat exchanger to heat the air to run the thing. Now, later on then, GE started out and reactors were actually run using the water-moderated nichrome fuel element thing. Engines were run and so forth starting in 1956, and I might say they were exactly on schedule. They were scheduled to run in January of 1956, and on January 31st of 1956, the first modified conventional jet engine was run on nuclear power under the General Electric Company. Something I would like to emphasize, during that period of development, there was continual, from NEPA all the way through GE until termination in 1961. There was a continual change in mission, which really didn't affect us as much as you might think, but the Fairchild project said, the NEPA people said, you have to demonstrate feasibility, operational feasibility. It isn't enough to be able to run an engine. You have to get in an airplane and show that it is, you can fly an airplane around, you can handle it on the airfield, and do one thing or another like that. You have to do that. So therefore, the mission would be to, okay, let's get a reactor and an engine developed, let's get a test bed, and let us fly it around for a few years, and so forth. Then a committee would come and they would propose that, gosh, we have to make it mission-oriented, so we want 60 or 100 airplanes. Then another, if you do that for a while, then another committee would say, no, we have to have this demonstration. It didn't really make too much difference. We kind of went along anyhow. Gradually, the configuration changed from the early demonstration of metallic fuel to ceramic fuel, and that's where it ended. And the later speakers will go into that in a great deal more detail.
Okay, Gunnar. What was the motivation of the project? And if it was so great, why do you suppose they terminated it?
Well, okay. I think what I'll do here is I'll pick up the key page out of the Fairchild, the NEPA final report, where they tried to, they have several items which they state as the motivation. And then I'll jump over to the GE termination report and explain a little bit about the endings. But the NEPA, in their summary, in the summary at the beginning of the report, page 5, it says that the motivation for development of nuclear airplanes was well understood amongst the highest circles of this nation's government is attested to by the following extracts from important documents. Okay, important document number 1. The President's Air Policy Commission on 1 January 1948, in its report, Survival in the Air Age, states, atomic propulsion. The possibility of employing atomic energy for the propulsion of aircraft and guided missiles is sufficiently important to warrant vigorous action by the Atomic Energy Commission, the Air Force, the Navy, and the NACA. Some work of a preliminary nature has already been done in this field by the AEC, the Air Force, and the NEPA project. Immediate steps should be taken to intensify research effort in this field under a plan which would be supported by all of the above agencies and under which the project would be given the benefit of all the background information in the atomic field actually needed by the recipients for the appropriate performance of their respective functions. Now, that was not a conclusion of contractors or Fairchild or anybody else. Let me remind you, that was the President's Air Policy Commission in January of 1948. So they came out at that time with strong support of what had been going on and that the nuclear-powered airplane investigation should continue. Okay. Important document number 1 was the executive branch of the government.
All right.
And now, that was the President's Air Policy Commission. Now, the congressional legislative branch of the government at about the same time. The Congressional Aviation Policy Board on 1 March 1948, 2 months later, in its report, National Aviation Policy states, the Nuclear Energy Propulsion for Aircraft, or NEPA project, should be accorded the highest priority in atomic energy research and development, and every needed resource and facility should be devoted to its early accomplishment. In the event of war or in any international situation likely to lead to war, nuclear energy for the propulsion of aircraft would be comparable in significance to the atomic bomb itself. Presently known limitations inherent in all chemical fuels make it difficult to deliver atomic bombs by air against a distant enemy. Therefore, if the United States had nuclear energy propulsion in addition to atomic bombs, it could be the dominant factor in maintaining world peace. Until these ends are attained, the United States must depend on military weapons and techniques currently available. We must therefore devote the best efforts of the national military establishment and the Atomic Energy Commission to the prosecution of the NEPA project to provide our armed services an effective method of accomplishing, without geographical limitations, immediate and devastating retaliation should our country be attacked. In addition to its military application, the successful solution of the problem of nuclear energy propulsion of aircraft will include vital contributions to human welfare of enormous value to our people.
Now, is this the time of the Berlin blockade?
I don't
It was
recall.
about the time of the
I
Berlin
don't
blockade.
recall.
Yeah, that was the Berlin blockade was taking place, and the situation with Russia was getting quite dangerous.
Right.
And the SAC programs, where we wanted to keep an aircraft, was they wanted to keep aircraft loaded,
Yeah, right,
aircraft in the air.
right.
constant 24 hours a day, put a real
Yeah.
pressure to develop such an aircraft
So you can see the motivation as viewed at the time.
at the time. All
It
right.
was very clear, and it was supported by both the executive and congressional branches of the government. Now, of course, some of the things that happened here is they talk about the limitations of present weapon systems. While the project was subsequently carried on, the conventional jet engines and so forth also continued to
Carry on.
to improve. And
And of course, then you had the beginning of the growth of bronze missile
yeah,
situation, which
right.
started
And the post-war development of those
Yeah,
things.
the post-war.
Okay, so that was the motivation that existed at the time of the NEPA project, and as summarized in the NEPA final report. And it's interesting that they make a point of that this could be the combination of nuclear energy propulsion in addition to atomic bombs could be the dominant factor in maintaining world peace, which is the point brought up in 1914 in the book by H.G. Wells.
During early 1951, the Joint Chiefs of Staff endorsed the military necessity of a nuclear-powered aircraft. The Air Force therefore scheduled the flying test bed to prove the concept. In March of '51, the Air Force awarded GE a contract to develop a nuclear turbojet engine. By June, the AEC also contracted with GE to develop the nuclear reactor. After several months of study, GE chose the direct air cycle concept, using an air-cooled reactor with metallic fuel elements. Water was to be both moderator and structural coolant. The resulting GE power plant, the P-1, was to be test flown in a B-36H, modified by Convair. Initial ground tests of the P-1 was scheduled for 1954 in Idaho. The test bed aircraft, designated the X-6, was to be flown in early 1957. The X-6 aircraft with the P-1 power plant was to evaluate the operational practicability of this system. Areas to be tested included shielding, propulsion, radiobiology, and radiation effects on aircraft components. The P-1 power plant, shown here, with 4 engines, the modified J-47s, with the ducting leading up to the reactor shield assembly. The compressor discharge went into the reactor and out, back through the ducting to the scroll at the turbine and out the rear. And now we'll have Buck Jordan discuss the reactor itself. Buck?
Just another word on this. The reactor essentially replaces the burner cans of the jet engine. The compressor exhaust into the reactor and back down in a high-pressure turbine through the exhaust nozzle to provide thrust for the engines.
But combustor cans were located in the pipes.
Yes. I'm going to speak a little bit about the reactor shield assembly. The shield assembly approximates a cylinder 10 feet in diameter and 20 feet long. It was essentially a tank of water surrounding the reactor core and reflector, which was 68 inches in diameter. This meant that there was 2.5 feet of water surrounding the entire core. The shield assembly is made up of the center section, the forward section, and the aft section. The forward section contained the instrument wells and was penetrated by the air ducts, both fore and aft. The reflector of this core was made up of 2 concentric rings, 304 stainless steel, which were water-cooled. The outer ring was a 3-inch ring of stainless steel. The inner ring was a 2-inch ring of stainless steel. The reflector was water-cooled.
And the airflow then was from right to left.
Right to left, correct.
Hey, we might say also that we use stainless steel. Stainless steel wasn't the reflector material of choice. We would really have liked to have beryllium, but beryllium at that time could not be fabricated in the sizes and shapes that we needed, so we ended up with stainless steel.
This is a schematic of the reactor assembly. The reactor assembly is essentially rings of moderator water, concentric with and alternating with rings of fuel elements in each one of these annular spaces. The moderator water flowed through the reactor and out through these moderator water tubes. The fuel elements were in trays longitudinally with a reflector, stainless steel reflector, water cooled. The outer reflector was 3 inches in thickness. The inner reflector was 2 inches in thickness. The fuel elements were in trays with 10 segments in each tray.
Those were on rails, weren't they, Buck?
The fuel element itself were 3.5 inches long, and there were 10 of them that were brazed to tracks that supported the fuel elements as they were slid into the reactor core itself.
And the moderator cooled, the water cooled the structure, which was of aluminum.
All the reactor structure was aluminum. These were the support struts for the moderator annular rings.
What was the nominal power of that?
It was a 150 megawatt reactor. It was designed for 150 megawatts.
Although 80 megawatt was probably the megawatts that would have been used.
This is a picture of a typical fuel element. The sheet material, or contained 78% of stainless steel and 38% of UO2. The cladding was a 4 mil 310 stainless steel material. The thickness of the plates varied between 11 mils and 16 mils to provide power flattening across the power distribution, flattening across the core. These largest fuel elements were toward the center, or the larger. This is the hydraulic diameter of the fuel element. About 3.5 inches at the center of the core and 9/10 of an inch at the outer periphery of the core. The plates were 8 inches long and 3.5 inches in depth. Each plate had fins brazed to the inner side and outer side of the plate, and then the corrugations were then brazed to these fins to supply support for the structure and also provide air flow area between the fuel elements. These fuel elements were tested, airflow tested, and also burner rig tested in the burner rig facilities at Evendale. Let's see. I think that's it.
Even though the R-1 reactor was never built, as far as the actual hardware was concerned, the reactor core itself was simulated in a critical experiment at Oak Ridge using, at the Oak Ridge table facility, what looks like this, wherein half the core is loaded in one half of the facility and the other half of the facility, and the two halves are brought together hydraulically to make the core critical. The matrix of the core, half the core looked like this. It was made up of blocks about 3 inches square of plexiglass and stainless steel impregnated fuel, UO2 fuel. These fuel element blocks look like this. They were plexiglass blocks on top and bottom, in between which was located the stainless steel and uranium fuel. These blocks were just slid in and out of the honeycomb matrix of the critical experiment. It was envisioned at one time that the actual reactor would be built up on a critical experiment, and that buildup would look something like this. This was never really done, but it does give you an idea of what the planning of the types of testing that were going to occur in the early stages of the program.
The weights envisioned for the reactor, the P1 power plant, the reactor itself about 10,000 pounds, the shielding around the reactor 60,000 pounds, the crew compartment, the shielding around it 37,000 pounds, the engines 18,000 pounds, the ducting and the structure 40,000 pounds, which made a total of 165,000 pounds that would go into the, for the total nuclear reactor system in the B-36H. Of course, fuel could be much less than the B-36. Some of the people that were involved in this were, like, I remember E.B. Delson in reactor design, and Carl Ockert, and Bruno Benini, Al Hinsey in controls and accessories, Charlie Jones worked on the aluminum rings, which was a real problem at that time because the aluminum available was certainly not what we have today. And Jerry Moore, the World War I pilot, always helpful. Certainly John Munday in manufacturing, Buck Jordan, Bob Evans, and any others that you can. Al Crocker, Bill Long, Al Crocker.
Corbin.
Yeah, Austin Corbin, Wally Thompson. Wes Schmill.
They could go down the list of people that were at A&P at the time, because that was virtually the only thing that was being worked on.
That's correct. Right.
Though a lot of the work, I guess, was done at Oak Ridge before GE moved up to Evendale.
Right. But the decisions, again, were remade by Miles Leverett and the rest of the people.
Can you say something about why it was terminated?
Yeah. In March of 1953, Stalin died. The Korean War was unresolved. Charlie Wilson, the Secretary of Defense, deciding on President Eisenhower's first budget, ruled that the flying testbed aircraft had no military worth. The X-6 program was therefore canceled, along with the P-1 power plant. However, a divided shield test using a B-36 was continued by Convair using a small 2-megawatt thermal reactor. Meanwhile, GE's effort was reduced to an R&D program. However, testing of the nuclear engines, the X-39s, on a common heat source was accomplished in Cincinnati. Hi. Today we're covering the X-39 engine that was used on the heaters 1, 2, and 3, and also some test work done here. And we're very pleased to have with us Jack Hope. And Jack, you came here with Gerhard Newman from Lynn, Massachusetts, down to Cincinnati. Back in what, 52?
Yes, well, I actually signed on with Gerhard in the fall of 51, and we came to Cincinnati in the early spring, February or March maybe of 1952, and carried out the program that we're going to talk about.
Good.
In fact, I think there was only about 4 of us in the group at the first.
Okay, go to it.
So the first engines that was used in the nuclear experiments, in fact the only ones used in nuclear experiments, was the X-39, and we have a picture of it here, if you can switch to the picture. The X-39 was a modified J-47, which was in production at GE at the time. And the key difference between the X-39 and the J-47 was that we were to remove air from the compressor and take it to the reactor, and then after the energy was added, heated, come back to another scroll to go out the back. This presented about a 30% pressure drop between the compressor and turbine, as opposed to 5% in a normal engine, and as a result we had to change the cycle. We chose to reduce the flow going through the compressor, so the X-39 compressor was cast with wall thicknesses about between 2 and 3 inches thick, and the blading was stayed the same, so that there was about 70 pounds a second going through the compressor, as opposed to 100 pounds per second in a J-47, and then, of course, the cycle was balanced. The greatest mechanical design job, of course, was in the scrolls. Now, in order to test this engine, we built a single-engine test cell at cell 33. I think it was in building 800. Had a big loop in it. So we had what we called a single-engine test cell, just a loop of pipe here with a bypass combustor in there to run the engine. And the main thing I remember about that was after working for several months, Gerhard and I and several other people were in the cell getting ready for our test. We had a Cadillac engine that was to drive through the bullet nose to start it. But just before we were to hook that up, there sat Gerhard doing this. And of course it ended up the Cadillac was going to turn the engine backwards, so we worked all night switching the input from the bullet nose down to a gearbox to get it started, and by the next day we had it running. We also had called one of the midgets that was at GE at the time to crawl through the pipe to make sure there was no obstruction in there, and the midget got there and looked at that and he said no, there's no way he was going through there. So guess who volunteered to crawl through the pipes? I was smaller then than I am now. But we built, I think we said 11 of these, and so they were run in a single engine test cell in Evendale, and also we had a single engine test cell in Idaho. But in addition then to running in the single engine test cell, we built at Evendale what we called the propulsion unit test cell. And this was to simulate a complete nuclear setup, only of course we were going to run on chemical power. I have a couple sketches here that show the inside of the cell. I believe at the time that was the largest engine test cell in the world. The idea being, another setup, we had 4 X-39 engines that the air was collected from the scrolls, went up to a simulated reactor, and then back through the bypass combustors, as we call them, to the turbine section. The reason for the bypass combustors was that in order to get the engine running, we would divert the air to just bypass the reactor, come back through this combustor, get the engine up to speed, and once it was running, then we would open the valves to run it through in this case, another combustor, or in Idaho, the reactor itself. Another reason for this configuration is, as you know, when you shut a nuclear reactor down, its energy doesn't stop immediately. In fact, I think you had planned to aftercool for maybe even days. With this configuration, we could start this combustor, continue to pump air through the reactor for as long as you wanted to run the engine, days at a time for that matter. Here's another picture of in the propulsion unit test cell that shows all 4 X-39s there with the 4 legs of pipe and the simulated reactor up here. We ran a lot of tests in the PUT cell. In fact, I have another photograph here, if it shows up. In this, we just had a single loop in here. This is how we tested the bypass combustor. We had one combustor running in front of another so that we could get simulated conditions out of the reactor to test the combustor. I remember when we finally got this fired up, and if the color will show up on the video, you can see that the first combustor is running very hot, supplying hot air to the second combustor, and then that's how we got the data for designing a combustor to operate under hot inlet conditions. I do also remember when we had that test running, Schiltz saw it and thought, boy, he was so impressed that he sent word all over Building D, and we was running at a waiting line of people waiting to come through to see that thing running hot. But we did get a lot of data from it. Then, of course, the thing we did after this test was to go to Idaho, and a lot of us I spent a complete summer out there helping the Indians build this up. They had a lot of Indians working in Idaho, and so our group, engine design, was responsible for the engines, the ducting, and the bypass burner, and the whole configuration. The first unit only had 2 engines instead of 4, and I like to think that that is a unique engine in my design experience, because I believe the power plant weighed 700 tons and put out about 500 pounds of thrust. So the thrust to weight ratio was atrocious, but it also had a 0 SFC. So we learned a lot from that. And the other thing I remember about that particular program was, I think it was after the first or second test, one of the fuel elements burned out in the core, and it scattered uranium out that big duct or smokestack. And they brought the power plant back into the hot shop, and then I hear that it's so hot. After they pulled the fuel elements out with remote handling equipment, put them in a pool, but it was so hot underneath the core that if they put their workers from Idaho in there to reload the core, they'd get a 3 months dose in 4 minutes. So I told Schiltz, well, why do you want to burn up those guys? Let me reload it. So we chartered a DC-3 and loaded it up with people from engine design and the new fuel elements, and took off for Idaho. So we got out there, and all of us guys in engine design, we practiced a whole day in a cold shop, getting the fuel elements up, rotating them in the instrumentation plugs, pulling them back down. So we went in the next day and reloaded that core. We each had a 4-minute time to do it. And I remember when we got done, Bill Long was so happy he threw a big party for us at the hotel there. So the other thing that's interesting about these, we had initials for all these. We had a single engine test cell, and it was called SET. Then we had the propulsion unit test cell, and it was called the PUT. And I remember the initial nuclear test we called the IET. And the funny thing is, for a few hours one time, we had the next test where we were going to fly we called it the Flight Aircraft Reactor Test. But that name got changed very fast because they didn't want to put the initials to it. I think that the only other aspect of the X-39 which didn't show in these photographs was the structural analysis of trying to transmit loads through a scroll was one of our biggest problems. Unsymmetrical pressure vessels are not easy to design. If you blow up a balloon, it goes round. So we spent a lot of money redesigning the scrolls on the X-39, the turbine scrolls, and that's what Don Riley did a lot of work on before the program was canceled.
Without computers.
With slide rules, that's right. Everything was slide rule. I still have my 20-inch slide rule with a magnifying glass on it. Another item of levity, if you will, is we were all crowded for space in A&P, and I had a small office in Building D, and as we got into the program, maybe I'd use this one here, Otto, we got squeezed and they moved 3 of the desks from the unit into my office. And so I said, well, we need more room, so I called in some of the engineers. You can see them here. There's Frank Gorsler, Russ Motzinger, Don Riley, Bob McDonald, Pete Dwyer. So we pretended we were working on a 2-level desk arrangement in my office and called a photographer. He took the picture. I gave it to Schiltz, and all he did was laugh, frame it, put it on the wall in his office, and I got squeezed a little more. So that didn't work. Another item of levity is for the first several years, we only had design groups. We had reactor design, shield design, engine design, and so forth. We did everything. But then they changed the organization eventually to where there was project groups. There was a project for Heater 1, Heater 2, and then, of course, the design groups. Well, I ended up with a design group, and this, I'm not sure if you can see it on there, the word, but essentially I found this on my desk one morning where all the guys in my group didn't think they were being treated right. So here is a model of a 2-story outhouse with engine design being on the bottom and the projects being on top. So I thought that was funny, and I've kept it all these years. The other thing we worked on a lot in engine design was configuration for the overall engine system, both the one that ended up with the X211 arrangement and also a nuclear turboprop study.
That went on for our first year or so of the NEPA life. And after that time, a number of us became more interested in the actual design of reactors. Wally Thompson worked very closely with me and was also a very good friend. He and I came up with the concept of using a water-moderated metallic reactor wherein the water kept the metal cool below melting point, and submitted a patent on that. So this patent was issued in the name of Wally Thompson and myself for the reactor, which actually was the reactor that powered the first turbojet. My next assignment after the efforts on reactor design, after I got to Cincinnati, we moved to Cincinnati in 1951, in D building without air conditioning, incidentally, in the summer. My assignment was to become a part of the Westward Ho task force. The task force of about a dozen people headed up by Jack Parker, who was working for Roy Schultz at the time, to establish the criteria, the fundamental criteria for the Idaho test station, the new Idaho test station to be used for testing power plants. Anyhow, from those preliminary criteria, the architect engineer went on to design the Idaho test station.
I want to first discuss the heat transfer reactor experiment number 1. The original objective of the ANP program, after we left Oak Ridge and moved to Cincinnati, was the design of a power plant to power the Convair X6 experimental airframe. The early availability rather than high performance was the primary requirement for this particular program. This work was authorized in 1952, but the whole direction was changed in 1953. The new objective was directed toward a broad spectrum of potentially useful nuclear propulsion systems, and the approach chosen by GE was to perform nuclear reactor experiments using reactor types with potential application to aircraft propulsion systems. These operations were designated as the Heat Transfer Reactor Experiments, and HTRE number 1 was the first of the series. HTRE number 1 and its successors were to be operated in a mobile facility known as the Core Test Facility. The Heater 1 is shown in this sketch, this artist's conception, as it was to be mounted in the Core Test Facility. The test vehicle was mounted on a 4-rail flat car and consisted of a shield tank, ducting, chemical combustors, and 2 modified J39 engines. The provisions were made for transmitting control information and acquiring data through an instrumentation and control plug mounted on the front of the CTF. The plug receptacle at the test facility accepted this plug and made the connections automatically. There were a number of specialized jigs and fixtures. That's the next chart, please. Designed to simplify the handling, loading, and unloading of the heat transfer reactors into the CTF. Next one. The CTF was assembled in the Idaho Test Station Maintenance and Assembly Facility, and this is a picture of that assembly in progress. The Heat Transfer Reactor number 1, as the first of a series, was to be a highly simplified reactor, primarily aimed at testing some of the key desirable features of future designs. Most important of these was power flattening, so that each fuel element would produce the same amount of power, and thus the entire reactor could be essentially isothermal. The design for the Heater 1 was based on the use of many of the materials that had been selected for the R-1 reactor. This is an artist's concept of the R-1. Specifically, water was to be used as the moderator, and aluminum as the principal core structural material. The configuration differed sharply in order to provide better structural characteristics and to simplify fabrication. The R-1 had been designed as a series of concentric annuli with the fuel elements contained in the air spaces between the annuli. The fuel elements themselves were to be a metallic material, or sheet metal, and in the particular case of the Heater 1, nichrome was selected as that material. The basic design of the reactor core was very similar to a fire tube boiler. The core was pierced by 37 tubes designed to hold the fuel elements. It was 30 inches across flats, and the hexagonal bundle itself was approximately, the fuel elements occupied approximately 28 inches of that bundle. The dynamic and shim control rods were housed in smaller aluminum tubes, which also served as inlet for the moderator water, which filled the entire vessel except for what was occupied by the fuel elements and the beryllium reflector. Water pressure was only that necessary for pressure drop due to pumping. And the water temperature was held around 160 degrees Fahrenheit. The individual fuel elements were made of rings of the clad metallic material. This is a sample element. These rings were joined into elements with a varying number of rings, depending on their location from front to back of the core. The 18 of these concentric rings formed a cartridge, and the cartridge itself had a nose section which was used to fasten it into the core, and a tail section which had access for a special tool that would go up and release the catch at the front to remove it. The cartridges were then placed in an insulated liner, which was then inserted into the core. Here's a cartridge in the process of being inserted, and here is a liner. Now these liners had a steel inner jacket. They were wrapped with insulation and covered with stainless steel foil. And the elements themselves were designed to operate at approximately 1700 degrees and produce an air temperature of about 1350 degrees Fahrenheit. And then to achieve the power flattening, the spacing of the tubes in the hexagon were varied because the flux would normally fall toward the outside so that the tubes were stretched further apart as you moved out, except at the beryllium reflector you had a reflux back in. So it took pretty careful adjustment to get the power right. Longitudinally down the cartridge, the number of rings were varied to hold the heat transfer roughly constant. It was very gratifying that the predicted fuel element temperatures and those measured in operation were in very good agreement, and this method of power flattening was used in all subsequent metal-fueled reactors. The Heater 1 program, was initiated immediately following the issuance of the 1953 program recommendations. the chart next. In September of '53, the button was pushed to start the program. By the following August, a mock-up, critical experiment mock-up, had been completed and the results achieved. And in September, we started releasing drawings for the manufacturing of the actual core itself. By August of '55, the manufacturing was completed, and we hired some couriers and got a caboose and a flat car and hauled it out to Idaho. In November of that year, we took that real reactor critical by itself. And then by January, it had been installed in the CTF and had gone to full power. By January of '57, the test series were complete. And it's very interesting that during this test series, I need the other chart. Yeah. That during the test series, all the principal goals were achieved. We ran in all a total of some 5,004 megawatt hours at power levels up to 20.2 megawatts, which is pretty darn good for a little thing 30 inches in diameter and 28, 29 inches long. 485.6 hours were above 200 kilowatts, and 150.8 hours were at full nuclear power. Now, the original goals had been to run 100 hours at full power. Unfortunately, during the first 6 hours of operation, there was damage to the fuel elements. Now, this damage was basically caused by the collapse of the insulation liners blocking the air passage and allowing the material to reach melting temperatures. One thing this put to rest almost immediately were the arguments that some people had raised against using aluminum backed up by water. This view shows the worst damaged cartridge from the side. Well, this was taken to the hot shop. We unloaded it. We redesigned the insulation liners, reloaded it, took it back to the initial engine test facility, and performed an endurance test of 100 hours with the discharge temperature at 1,280 degrees Fahrenheit, which was ample to run the modified J39 engines, and then ran it 44 hours beyond that at 100 degrees higher temperature at 1,380. The objective of the test was 100 hours at full power. So all of the objectives of the program in terms of the design for power flattening, in terms of the design for operation, were either met or exceeded. And the feasibility of operating a nuclear turbojet engine with a direct air cycle reactor was demonstrated. And this was the first known operation of a high temperature gas turbine engine on nuclear power. Certainly looks its age in that picture. And that ran regularly between Wilmington and Idaho Falls. This is a sight flight again with a group preparing to leave Wilmington to head for Idaho Falls. And that is the story of the Heater 1.
Very good.
We're going to spend a few minutes giving definitions of what various terms mean you're going to hear throughout the discussions of the A&P program. We'll start out here with power plant. Next is the concept of a thermal reactor. Next is the definition of what a critical reactor is. I'm not going to really describe these terms because it's much easier to just read what it says. And of course you'll have this for reference as time goes on. What is fission? What is a moderator? What is a reflector? What is a control rod? What is a safety rod? What is a neutron? What is neutron flux? What is a barn? What is a cross section? In relation to cross-section, here are some cross-sections of some typical materials used in the A&P program. And What is multiplication factor? And finally, some facts about uranium-235.
I made my first trip to what eventually became the Idaho Test Station in early 1951. I mean very early, when the temperature was about 30 below zero. The selection of that as the site for GE's test station was made in the 51-52 period. Construction of facilities proceeded very rapidly and was well underway by the end of 1953. The most challenging of the facilities, and it was started early, was the assembly and maintenance area, better known as the hot shop. And we're ready for that chart. The hot shop consisted of two major buildings, an assembly and maintenance area, which was known as the cold shop, and the hot shop itself, which was a high bay area with shielded walls, shielded windows, and the shielding was sufficient for any of the projected reactors, including the aircraft reactor, to be bare within those walls. It was equipped with turntables. It was equipped with standard manipulators, and it was equipped with one special manipulator. The manipulators were operated from behind shielded windows. These windows were approximately 8 feet thick, and they were a combination of leaded glass and a special liquid. The particular manipulators in the area. You had the small ones that you saw the man operating from behind the window, but there's one very special one known as the O-Man. The O-Man was designed and built in Schenectady by GE. It was one of the first of the servo manipulators, in that there was actual feel back to the hands of the operator, who wore special handling gloves, and he could adjust his pressure so that with this particular manipulator you could either pick up an egg or lift several hundred pounds. Also under development at that particular time to aid in viewing was a 3D stereo television camera, which was one of the first areas where such a device was used. Behind the windows here and at one of the stations, you see most of the upper brass of GE ANPD. This is Frank McCune, the Atomic Division General Manager. Next to him is Jim Lapierre. Next to Jim is Wayne Lapierre. Excuse me, is Wayne Perry, who was the manager of the Idaho test station, and next to him, Roy Schiltz, the general manager of the department. And in addition to the general purpose manipulators and the O-Man, the hot shop and the assembly and maintenance area were both served by the four-rail track system, which went to a turntable, from the turntable to the initial engine test facility, and ultimately was designed to go to the flight engine test facility. Along with the permanent facilities, there were mobile facilities like the shielded locomotive that was used to move the various test vehicles from their facilities. It needed to be shielded because the shielding on all projected reactors was to be fairly light, since the crew was to be shielded in a special crew shield in the aircraft. And there were some other early buildings built here. The single engine test facility was a facility built to just test single engines prior to assembly onto the CTF. We also built a low-power test facility, which was a critical experiment facility, and next to it was a shield test facility, which provided for tests of sections of shields, both in a water tank and from towers where it could be suspended. The extremely important to the overall program was the initial engine test facility. It had an underground control room, it had a test cell and an exhaust stack, and you can see the connection on the four-rail trackage back to the turntable. This facility, the underground control room, could be accessed through a 450-foot tunnel since the radiation levels when running at full power were too high to approach it directly. The test cell itself was covered by a movable shed which rolled on tracks outside of the four-rail track system, and it was connected to a stack through a series of electrostatic precipitators. The engines on the CTF would plug directly into the receptacle ducts that led to the precipitator in the stack, and the plug contained all the necessary instrumentation leads and control leads from the core test facility. Now this shows the core test facility as plugged in with the shed removed. Inside of the control room was what at that time was an up-to-date, state-of-the-art data processing system which could handle 500 pieces of data and could reduce them in a minute to a half dozen important parameters. Beyond that, there was a control panel from which you could control the reactor and the engines and the other functions on the CTF. The IET was the test facility for the entire series of heat transfer reactor experiments. The final facility that was built at Idaho was the Flight Engine Test Facility, which is one of the largest single-span poured concrete buildings ever built. It allowed for a clear span of some 300 feet for the wings of the projected aircraft and a tail height of approximately 90 feet. It had an underground control room. It could be approached through roughly a mile of underground tunnel, and it would have been connected to the hot shop with the four-rail system, and ultimately it was planned to build a ramp in the front with a taxiway out to a 15,000-foot airstrip, for which, incidentally, all the test borings had been made and the strip was designed. Also, along with that, there were a number of studies done on flight patterns from Idaho to a clear ocean test area. And as an adjunct to the FET, a shielded vehicle known as the Beetle was designed and built. Now the purpose of the Beetle primarily was for the installation and removal of the test engines, either from an aircraft or an aircraft mock-up in the FET. Actually, the Beetle was completed even after the closure of ANP, and ultimately it was used in the cleanup of the SL-1 disaster in Idaho Falls and then shipped to Jackass Flats, where it was used to pick up the spillings out of the Nerva rocket reactor. This is another shot of the Beetle, fully extended. And finally, here's a shot of the Beetle on the rollout day with Colonel Standifer of the Air Force doing the honors of swinging the young lady. In 1988, December of that year, the CTF and the Heater 3 were moved from the ANP site down to the old experimental breeder reactor site, which was 31 miles south. And this was to make them available for public display, because the ANP site, which is now known as the Test Area North, is still very active. This picture shows the transport as it went down that 31 miles of road. It was on a trailer with 144 tires spread over 12 axles, and the darn thing weighed 600,000 pounds. So if you want to see it, you can go to Idaho Falls and visit it right now.
HTRE2 reactor design was essentially an offshoot of the Heater 1 design. And the Heater 1, of course, was as Bill Long explained earlier, was a 30-tube water-moderated beryllium-reflected reactor. This gives you some idea of what the overall configuration looked like. We have the 30 tubes in an aluminum can surrounded by a beryllium reflector and containing water, which was a coolant, pumped through these pipes. And the 30 fuel elements were inserted from the bottom, and they occupied about 30 inches of the center section of the core, right in the middle of the reflector. In the process of building up the core, the system was fitted into a series of jigs. We can see the top tube sheet and the bottom tube sheet with the control rod aluminum tubes sticking up through the tube sheets. This thing was assembled gradually as the parts were made available, and of course it was assembled from the inside out. This picture gives you some idea of what a side view of the system looks like, with part of the reflector installed. This was a 4-inch thick reflector, loaded up. Here's the bottom of basically the bottom of the core, and there was another section stacked on top of that. Here's another view of as the assembly progressed, looking down again on the beryllium reflector segment of the core. Remembering this is important because when the Heater 2 was designed, it was concluded that in order to get the power densities up in the center section of the core, it would be necessary to increase the thickness of that reflector from its Heater 1 thickness of 4 inches to Heater 2 thickness of 8 inches. And we can see that difference here with a similar buildup of the Heater 2 reactor showing the center cutout of 11 1/4 inches and the 8-inch thick reflector. The reflector is fully installed here. Incidentally, the manufacturing of the cover or outer section of the tank was really a unique manufacturing job. They took a sheet of either 1/4 inch or 3/4 inch or 1 inch aluminum and put it on a brake press and just kept pressing it until the flat sheet was circular. It was kind of ingenious. And of course, the Heater 1 fuel element looked like this. It was a concentric ring fuel element with a 18 stages of approximately 1.5 inch thick concentric sections stacked onto an assembly that would allow remote insertion and removal from the reactor core. The Heater 2, the Heater 1, of course, the design having been completed at the time of the design of the Heater 2, pretty much of the Heater 2 design characteristics were already established. The fuel elements were basically the same. We're going to be talking for the next few minutes about the HTRE2 reactor as it was operated, built and operated during the ANP program that was controlled and operated by the General Electric Company. The Heater 2 reactor was started and designed in 1956 and first tested in 1957 and ran throughout the length of the program until it was terminated in 1961. A brief history of the reactors in the ANP program. The R-1 reactor was the initial reactor studied. It was a design that was transferred up from Oak Ridge, the old NEPA project, in 1951. It was studied for about 2 years, at which time the program was redirected. And the Heater 1 reactor was started. The design started in 1953. The objective of the Heater 1 reactor was to try and demonstrate that we could actually operate a turbojet engine on heat produced by a nuclear reactor. That reactor was tested in 1956, at which time 2 other reactors the design was started on. The decision was made to move away from a water moderated reactor because of the inherent problems in flying water moderated systems. And secondly, Heater 2 design was started in order to test larger segments of reactors compared to what could be tested in the various materials test reactors and the engineering test reactors at Idaho. The Heater 3 reactor was the design envisioned to eliminate the water, which used a hydride zirconium moderator instead of water. And that design was also started in 1956. The Heater 2 was operated, as I pointed out, from 1957 through 1961. And it provided a whole series of materials tests, the results of which were used to design not only the Heater 3 reactor, but also the ultimate reactor in the GE program, the ceramic reactor 104E. The design of the 104E was started in 1960 and was underway just prior to termination of the program, and of course everything came to a halt at that point. We'll take a few minutes to look at some of the design features of the Heater 2 reactor. Most of what we're going to be talking about the rest of the day are what the Heater 2 design looked like and what the tests accomplished. It was one of the most successful programs in the ANP program as far as total reactor operation is concerned and as far as the results generated is concerned. The Heater 2 reactor is basically a redesigned Heater 1 reactor with a center plug cut out of the Heater 1 plug and a center fuel and moderator section cut out of the center of the Heater 1 core. The idea being, of course, to be able to build an insert assembly that could be removed remotely and have the insert materials changed and then reinstalled in the reactor and operated again to get test results. The actual plug, the photograph, the actual plug looks like this, where we have the plug assembly made out of steel with cooling water and an insert assembly, which could be removed and changed at the designer's will, and the instrumentation section up here to record results. This device, this insert, of course, being removed and installed remotely because the materials, after they're exposed in the reactor, are pretty hot nuclearly, making a lot of gamma radiation. The top tube sheet of the Heater 2 looked like this. There were 30 tubes of the Heater 1 design, exact same design configuration. The center section was, a hex segment was cut out to allow the insert to be installed through the top of the core. This was about 12 inches across. The whole core is a little over 30 inches across. The fuel elements in the outer 30 tubes are identical to the Heater 1 fuel elements, modified slightly to take account of Heater 1 test results. Nichrome cladding over uranium oxide fuel. To get some idea of the relationship between the so-called inserts in the parent core, we've got a chart over here that shows basically what the Heater 2 top tube sheet looks like, with the realizing that this originally was a Heater 1 top tube sheet with the center section cut out to allow the insertion of the insert sections. This cutout was about 11.5 inches. There were three basic types of inserts tested: the insert 1B, insert 2B, and the so-called cartridge type insert. The insert 1B, of course, being the 7 tubes of zirconium hydride and metal fuel elements. The insert 2B being a insert made up of round beryllium oxide fueled and unfueled tubes with beryllium oxide slabs. And because of the fact that we're getting relatively low power densities in the insert region for these first two inserts, we designed an insert that would give us a boosted power density in a smaller insert section by building a metal or aluminum can with beryllium slabs that would boost the neutron flux in the central region. And you can see by comparison, we're talking roughly a 4.5 foot section compared to an 11.5 inch. This is a 4.5 inch section compared to an 11-inch section up here. And the types of testing that were done here were the so-called cartridge tests, of which there were approximately 9, and we'll be discussing those in detail later. The first insert tested was, as I said, was a zirconium hydride insert. We had 7 zirconium hydride tubes, 7 fuel elements. They're essentially basically the same design as the Heater 1 concentric ring, nichrome type fuel elements that look like this. The second insert tested was a ceramic insert test, which involved testing of beryllium oxide round tubes, some of which were impregnated with uranium oxide fuel. These tubes in a bundle look basically like this, stacked up on top like this, and there were about 10 layers, 7 of which, there were about 12 layers, 7 of which were, no, 10 layers. There were 7 of which were fueled, and the top and bottom layers were unfueled, acting as reflectors. And there was a beryllium oxide slabs containing the whole structure. This was envisioned as the basic design segment of the 140E reactor, the full-size ceramic reactor. In looking at the slab and tube design, this particular design didn't come out of the blue. It was a section, the insert 2B, was a section of a full-size reactor that was basically designed to look like this. You can see that this center piece here pretty closely represents the way the insert 2B looked as it was inserted in the reactor. And of course the whole reactor itself was built up of just layers and layers, or segments and segments of the, this is a mock-up for mechanical testing purposes. At a point in time, we came to the conclusion, after testing those first two full-sized inserts, we call them full-size inserts, we came to the conclusion that we weren't getting high enough power densities in the insert region. We would run the reactor up to power, and before we could get the test conditions that we desired in the insert, we'd reach a limiting fuel element temperature on one of the outer fuel tubes in the parent core. We came up with a solution to that problem, and that was to build an insert that had the basic same size to fit the hexagonal hole, but it included a can that had a bunch of beryllium slabs stacked in the can and water cooled, and with a central hole that would contain the test cartridges. And of course these test cartridges were considerably smaller than the full-size insert, but we felt that the process was needed in order to get the power levels up. The relative size of that test cartridge looked like this. This is a bottom tube sheet off of one of the ceramic test cartridges we'll talk about a little bit later. The tubes being stacked up on a cartridge that looked like that. This is still a lot bigger than what we could test under this kind of conditions that we wanted to test in the engineering test reactor or the materials test reactors. Of course, the testing was conducted in the same facility that was used to test the Heater 1. This was the so-called core test facility, which was a big platform. I'll show you a picture of it in a minute. That contained a vessel that in which was housed the basic Heater 1 type core. This is a picture of the Heater 1 setup, with the turbojet engines supplying air through ducts into the top of the core, the air going through the core, picking up heat and being ducted back out to the turbine of the turbojet. The turbojet, of course, had to be started on chemical fuel, and as the reactor power was brought up, the chemical fuel process was turned back, just like turning down a burner. To the extent that at the nominal powers that we're running the Heater 2 at, we were essentially providing all the heat to a single turbojet engine. And photographically, this is what the nice pretty color picture of what the core test facility looked like. This is the jet engine we were talking about. And this is the duct that took the compressor discharge air into the top of the reactor core. And this is the plenum that brought the hot air back into the turbine of the engine. This whole device was moved on a set of railroad tracks by a locomotive here that was especially designed for this program. It's heavily shielded to protect the operator as he moved the core test facility up and down the track. And of course, the reason for the track was the actual test building was about 1.5 miles or 2 miles away from the so-called hot shop, where all the examination and disassembly of the cores was done. The Idaho test facility we talked about is the place where all this testing was done. This picture is not a very good picture, but it shows you get some idea. It's out in the desert. There was an underground bunker that was covered with dirt where people entered, went down to a control room. The control room had access through tunnels to the initial engine test facility, which was a sheet metal shed that could be slid back and forth. And the discharge of the jet engines went out through a long pipe to a smokestack. During operation of the reactor, it was very important to pay close attention to which way the winds were blowing. There was always a potential of radioactive release from the operation of the reactors, and we wanted to make sure that if whatever release got out would go be deposited on those parts of the desert that there was virtually no populations. The types of testing, there were two types of testing, as I alluded to earlier. There were full-size inserts, and then there were so-called cartridges, which are those smaller segments that went into that redesigned insert with the beryllium slabs. We tested 4 inserts for a total of 256 hours, one of which was ceramic and one of which was a zirconium hydride moderated insert. We tested 9 cartridges for a total of 1,087 hours, where a total of megawatt hours of 12,332. The nominal reactor power during all this testing was somewhere between 12 and 15 megawatts. As I mentioned, the testing of this reactor provided essentially all the design information from the standpoint of materials tests that were used in all the future reactor designs for the aircraft propulsion at GE and Evendale at the ANP program. Let's spend a few minutes talking about what the results of some of these tests were and how they impacted the program. The insert 1B was the 7-section hydrided zirconium insert with 7 stainless steel clad zirconium hydride bars loaded with the concentric ring fuel elements. As this reactor was started and testing proceeded, it was very apparent that we couldn't get the test conditions especially in the moderator material that we desired, and we were looking for temperatures in the neighborhood of 1650 degree F moderator temperatures. And the general conclusion was that there wasn't much reason to continue this test, and it was concluded early and sent back to the shop for examination. The second insert was a first in a series of many tests on beryllium oxide tubes. As the examination or design analysis went on and program philosophy evolved, it became apparent that probably the only way we were ever going to get something that really approximated a true flight type reactor was go to a ceramic type fuel element. There was therefore a lot of emphasis placed on the development of ceramic type materials. The first testing was done on these round type beryllium oxide tubes impregnated with uranium oxide. That testing was commenced, and at the outset we came to the conclusion that it was a gross misdistribution of air between the parent core and the insert. We just couldn't get the temperatures up in the central part of the insert assembly. The reactor was returned to the hot shop several times to provide plugs to that tube sheet on top of the core. This is a tube sheet made out of Inconel with little holes punched in the top to allow the air to get through to get into the BEO part for cooling. Eventually, we were able to get temperatures up in the core in the neighborhood of 2,750 degrees F, which was our design target. And we commenced to operate the reactor. As we monitored the test results, two things were happening. The temperatures started to, on the thermocouples that we had available, started to increase, and the thermocouples started to fail. And also we started picking up fission product, indication of fission product release on our stack monitors. This became a point of concern. There was always a concern that with an uncoated fuel tube that we probably would get fission product release. It was decided, however, to continue the reactor operation in order to accumulate time on that particular type of material. And as time went on, the temperatures continued to increase, and at some point we finally lost all the thermocouples in the core. We did, however, complete 100 hours of testing, 25 of which was at temperatures in the order of 2550 degrees F, and 100 hours at temperatures over 2800 degrees F. The core was returned to the hot shop for examination. As the reactor was unstacked layer by layer, we started to discover, the first thing we observed was there was almost a total loss of fuel in the lower fuel tubes in the insert section. The tubes were essentially bleached white, which indicated to the designers that the reactor, that part of the core, was probably operating over 3,200 degrees, which was considered a temperature required to boil that fuel out. As we continued to unstack the core, we started to notice the presence of a lot of crystals. And in fact, crystals in a quantity sufficient to essentially block the air to the fuel tubes. And it became apparent that this was one of the reasons that their temperatures were increasing as time went on, that the tubes were being blocked and the cooling air was prevented from getting to the fuel elements. As a result of that, of course, the big question is, why was that happening? And boy, that's not a good thing to happen if you're going to design a ceramic reactor. And the eventual conclusion was, after the materials guys had done a pretty in-depth analysis, was that we were basically hydrolyzing the beryllium oxide at the top of the core and then redepositing it in cool regions in the hot section of the core. And these crystals especially were noted at the joints of the tubes. If you could take a look at what I mean by a joint, where the tubes come together, the stacks of tubes come together, they form a joint. And it was apparent after some analysis that the air was getting down the interstices of the tubes. What I mean by that if you hold a bundle of tubes up, you'll see that there's a little gap right where the tubes come together. And the air was getting down in between the tubes, and it was coming out at the joints. And where it was coming out at these joints, it was cooling the joint, and therefore we were getting these crystal buildups. Well, of course, this is a revelation. Obviously, we're not going to build a reactor that's going to operate at the temperatures we'd like it to operate at and kick out fuel element or uranium fuel and fission products. So the emphasis was placed on trying to find some way of coating the tubes on the ID to prevent this fission product release from taking place. The next insert we tested was another zirconium hydride insert, but in this insert the stainless steel cladding was removed and the tubes, the zirconium hex sections were slotted to improve the heat transfer. This reactor was operated. We got 1200 degree F on the moderator. However, we almost immediately ran into a problem. We started getting indications of fission product release, and the fear was that we had ruptured some fuel elements in the concentric ring fuel. So the reactor was taken back to the hot shop and it was examined. And it was discovered that the fission product release was basically due to the deposit of uranium oxide in the lower plenum of the core test facility due to the previous test, the ceramic test where we had boiled off all the fuel from some of the lower fuel tubes. And this fuel had deposited, UO2, had deposited in the plenum and was actually fissioning in the lower plenum. The inability to achieve the desired moderator temperature was again determined to be partially due to the fact that we couldn't get the power distributions, the power densities that we'd like to get in these full-sized inserts. The last of the full-sized inserts was essentially a copy of the zirconium hydride insert with the unclad moderator, except this time a beryllium oxide or a beryllium bar was inserted in place of the central tube, the central fuel tube, and the desire here was to increase the core flux. And also, the primary reason this particular insert was run was to evaluate a hazards condition that would result from the total blockage of air to one of the fuel tubes. This test was run. The air to the tube was blocked remotely by an automatic valve over one of the tubes. And the reactor was taken back to the hot shop for examination. The examination showed that in the process of blocking this one tube, it had essentially overheated to the point that a lower section of the tube dropped out. Like the support structure had failed and the tube had dropped out and was caught in the lower support structure of the fuel element. And in addition, the fuel elements had melted, some of the melt had gone out into the reactor plenum. And in general, the testing essentially revealed what the characteristics of what a melt would be. Of course, this went into the history file for future evaluation at the time the Heater 3 reactor went to test, or would go to test. The conclusion of the reality that we were having severe problems in getting our power densities up in the full-size inserts, of course, led us to go to the design of the cartridge type insert. The first of the cartridge tests was going back to the ceramic reactor concept again, using round beryllium oxide tubes stacked in the hexagonal array around the aft tube sheet. And this again, I'll just show you this as the concept of what the stacking process looked like. We had the tube sheet, and these tubes were stacked over these holes, one on top of the other, until we had our full insert assembly. The reactor was operated for 100 hours at temperatures above 2,500 degrees F. And of course, the primary purpose was to quantify what was going on in the previous insert from the standpoint of the crystal growth, the air blockage, and the temperatures that were involved. And again, we were trying to duplicate the beryllium oxide transportation, or the hydrolysis of the beryllium oxide and transportation down and redeposited as crystals farther down the tube. And also there's a question of, what's a realistic operating temperature for an uncoated beryllium oxide tube. The test was completed and the insert was taken back to the hot shop and the cartridge removed. And we observed the crystal growth in the same places that we observed it in the previous test, in the full-sized insert. Again, the trailing edge, indicating the cross flow in the round tubes. And again, we measured efficient product release as time went on. As testing increased, efficient product release increased. Well, this is kind of significant from the fact that you conclude there's migration across the fuel tube, and as the temperature time history of the core increases, you get efficient product release increase. This essentially confirmed the notion that we probably weren't going to operate any ceramic reactors with uncoated tubes. And the desire then was to try to find out something you could coat these tubes with so that you could prevent not only the hydrolysis of the beryllium oxide, but also the prevent the fission product release. The second test of the cartridge type was with a zirconium hydride moderated fuel tube assembly again, but this was the so-called XMA1, which was the first zirconium hydride type flight type reactor design. The hydride, the specs on this particular cartridge were the specs that would be given for the flight type reactor. This particular design had a round concentric ring fuel element, but the materials were a little bit different. They were chromium UO2 titanium core material, which previously was essentially UO2 and nichrome, with an iron chromium yttrium cladding. This reactor was operated for a period of time at peak temperatures up to around 2100 degrees F. We did detect fission product release again, and this again resulted in the termination of a metal ring test where we were again afraid of blistering or rupture of the metal rings. Reactor was removed back to the hot shop again for examination. And this examination did show that many of the fuel stages, the concentric ring fuel elements, had blistered, and in fact some had ruptured, which of course would have explained why we were getting fission product release throughout the period of the testing. This information was fed back to the materials guys who used it to evaluate the design characteristics and the effectiveness of this new type material, fuel element material. The next cartridge went back to round ceramic tubes again, but this time the tubes were coated on the ID with aluminum oxide. The coating, I think, was approximately 3 mils thick. They were both unfueled and fueled tubes, the unfueled tubes acting as top and bottom reflectors. The tubes were contained in an insulation liner in order to minimize the heat loss to the parent core or to the parent insert in this case. And this cartridge was operated at a maximum temperature of about 2,500 degrees, producing a maximum power in the insert of about 300,000 watts. This in itself is a significant thing because you got an insert that's a fuel section of a cartridge that's essentially 30 inches long and about 4.5 inches across its flats. If you can imagine that size of a piece of material, UO2 fuel producing 300,000 watts, you come to the realization of just what the power producing capability of uranium fuel is, enriched uranium fuel. This particular cartridge also had a radial variation in the fuel loading, and the objective here was to try to obtain a flat temperature profile across the cartridge. Of course, results of earlier testing on cartridges indicated that we were getting a slight distortion in the radial profile, and the desire was to try to flatten that out. The test was operated for 106 hours at a temperature above 2,500 degrees F in order to evaluate what the effect of that coating was. Reactor was returned to the hot shop for examination. No beryllium oxide migration was detected, and no crystal growth was found, which is all right. We got a nice indication that the coating is working pretty good. However, we did find streaks, tan streaks outside of the tubes, again suggesting that we're still getting this interstitial flow through these round tubes. We did get some fission product release, though it was much less than previous testing. Got a little picture here to give you some idea of what the some of these tubes look like in the previous test where we're talking about the crystal growth. And you can see at the trailing edge of these tubes this white material that's building up in these areas. This is a kind of blockage that we experienced during this type of testing. Well, the general result of this particular test and the previous two tests was that interstitial flow is a problem. Round tubes are a problem. So the obvious choice was to try to come up with a tube that would essentially eliminate the interstitial flow, and this would be a hexagonal tube which would essentially fill up all the gaps. This chart gives you, or picture gives you an idea of how the round BEO, or the hexagonal BEO tubes were stacked up to, these are incidentally fuel tubes. You can see the dark color. that the tube turns when the uranium oxide is added to it. These tubes are also coated on the ID with, I think it's aluminum oxide. And this is what the hexagonal type tube looks like. And you can see that when you stack them all together, there's no interstitial little holes for the air to move down. So the process of going to a hexagonal type tube was the next point on the development curve of the ceramic tubes, ceramic reactors. And the cartridge was built with hexagonal beryllium oxide tubes, which were coated on the ID with zirconia this time, ZrO2. We're trying different types of coatings to see which is more effective, aluminum, zirconia. Again, about 2 or 3 mils thick. The reactor was, of course, the purpose of the test was to evaluate a zirconium oxide coating as compared to aluminum oxide relative to fission product release and hydrolysis generation. This reactor was operated for a total of 102 hours above 2,500 degrees and 102 hours above 2,600 degrees. However, there was some flow restriction required in order to achieve these test conditions. The little pins had to be put in to get the temperatures correct. This reactor was taken back to the hot shop and examined, disassembled and examined. The core was, or the insert was. We found no blockage, no crystal growth, no cracked or broken tubes. We did have some reddish color on the ends of the tubes, but we couldn't identify what was causing that. There was some blistering observed between the fuel and the zirconium coating. This information was fed back, of course, to the materials guys to figure out what was going on and see if they could improve the design. The next cartridge tested was basically the same as the previous one, except instead of a zirconium oxide coating, it had an aluminum oxide coating. So now we have a hex tube with an aluminum oxide coating. We also went to a slightly smaller tube, and we did another thing for the first time, and that was to stagger the rows. And by staggering, I mean that whereas if you take a bunch of tubes and stack them unstaggered, you'll have two rows essentially butting, two stages essentially butting each other like this, so that you have a gap. You could have a gap between the two stages. By staggering the tubes, every adjacent row was set at a little different height, so that no two tubes ever lined up at the joint. And of course, this was done to try to minimize the crossflow process. The loading again was varied radially to try to flatten the temperature profile. Again, we were trying to evaluate what the effectiveness of aluminum oxide coating was. The reactor was operated for 46 hours at 2,500 degrees F and 99 hours at 2,600 degrees F. When we talk these reactor operations, we're talking 200,000 to 300,000 watts in those generated in those insert sections. We did achieve a flat temperature profile for the first time, and of course this is much desired because you can get a better evaluation of what the tubes are doing if they're all running at the same temperature side by side. Post-test examination showed no crystal growth, no cracks were observed. There were some cracks observed in some of the tubes, and after the test it was generally concluded that this was probably due to an inferior grade of beryllium oxide. We did have an increase in fission products during the test. This was probably due to the cracks, the cracked tubes, fission products leaking out through those cracks. The next cartridge in the line of beryllium oxide testing, practically everything from here on throughout the remainder of the heater tube program was beryllium oxide testing. we're getting to the point now we want to finalize the basic design and materials content of the 140E reactor. Again, this was hexagonal fuel tubes and unfueled tubes acting as the top and bottom reflectors, with a zirconium coating on some and an aluminum coating on others. This particular test was operated in order to evaluate a hazards condition if some of the tubes had been plugged or were plugged due to inadvertent damage or plugging at the air source for some other reason. Reactor was, the testing was terminated after about 850 seconds when we had got an inadvertent scram. The sensors, we believe, detected some kind of an excursion due to efficient product release coming out the back end of the reactor, and interpreted that as an unacceptable period on the increase the reactor power and shut the reactor down. This test was repeated, except a desire was to essentially change the cooling characteristics a little bit. The central tubes were still plugged, but the outer two rings, some air was allowed through those the outer rings were unplugged, and some air was allowed through the central plugged region. There was about 10% of the air was allowed to go through it. The hex tubes had no ID coating. The object here was to see what the differences between an uncoated tube and a coated tube would be under these meltdown conditions. The objective here was the same as the previous test. In order, we wanted to find out what the effect of a blockage condition would be on the ceramic tubes. Maximum temperature in that particular region of the reactor probably was in excess of 3,900 degrees. Yeah. Though for this particular test, we measure reactivity on these limited melt experiments to find out what the effect of losing fuel is on the reactor core. Also, we want to know if we lose fuel, how much is that going to cost us in excess reactivity? And this particular test indicated that we didn't lose any reactivity. So the indication was we didn't lose any fuel. Hot shop examination showed that practically all the tubes showed no, the tubes outside the unplugged tube showed no evidence of melting. The block tubes did have heavy deposits of white crystals. Now, of course, remember, these were unfueled tubes, or uncoated tubes on the idea, so we were pretty confident we were going to get the hydrolysis problem reappearing. The white crystals turned out to be, of course, beryllium oxide. In some cases, yttrium oxide, which was installed in some of these tubes as a binder or as a mixture with the uranium oxide. The rear grid plate for this test was intact, indicating that we had not melted a lot of fuel out of the center region. Some fuel tubes were cracked and some were shattered. But the basic result of this testing was that we gained a high degree of confidence that if we did block the air to a small section of the reactor for whatever reason, we could feel reasonably confident that propagation wouldn't spread throughout the reactor. It'd be relatively well confined. The final test in the series, the cartridge test series, which basically brought us to the end of the A&P program, was kind of a proof test on hexagonal fuel tubes with a ID coating of zirconium oxide. All fuel distribution is varied across the flat to give us a flat temperature profile. None of the tubes were blocked. The reactor was operated at temperatures in the neighborhood of 2,650 degrees F for a period over 300 hours. Time was, the desire here was, well, we thought we were pretty close to having what we think is a final design on a ceramic fuel tube. We wanted to accumulate a lot of time, measure fission product release as a function of time, measure, and of course after a shutdown, determine what if anything happened to the tubes operating at this temperature. We had one small problem during the operation. As time went on, and we had a couple of shutdowns during the testing, and this is 200 type hours, we were getting xenon buildup in the parent reactor core that became high enough to prevent us from making the reactor critical. We couldn't override the xenon with the control system we had. But fortunately, as we had talked earlier in previous discussions, we were able to raise the moderator temperature to about 200 degrees F. And since this reactor has a positive temperature coefficient for reactivity, we were able to achieve enough reactivity in the system in order to get it up on its period, or get it up to power. Of course, once you get to power on a reactor, you tend to burn that xenon off and you gain your excess reactivity back. We desired to measure fission product release as a function of time and temperature. We found as a result of this that we had increased the fission product release by a factor of 2 between 2600 and 2700 degrees F, but we increased it by a factor of 10 in going from 27 to 2800 degrees F. Of course, this is a significant. We're still releasing fission products. This is going to be a continued design problem when you put a type of reactor like this in the air. Chances are pretty good you're probably going to continue to release fission products, unless a new coating could be discovered that would totally prevent fission product release. The general appearance of the tubes was good. There were no broken tubes. There's no broken unfueled tubes. There were some broken fueled tubes. There was some blistering in the cladding again. All these things we had observed. In this particular test, there was an unfortunate occurrence. There was, after the examination and post-test analysis was started, we discovered there was a small piece of fiberglass or glass insulation laying on top of the cartridge assembly, which could have affected the airflow to some of the tubes. In all, though, the general result was very good. There was, I think, enough confidence as a result of this test to continue to proceed with the design of the ceramic reactor, which of course was the intent with the 140E reactor design, which was started in 1960. The program was terminated in 1961, and all testing on the Heater 2 reactor and any other reactor was also terminated. We have here a picture of some of the people, especially in the manufacturing end, that worked on the Heater 2 reactor. A lot of them you probably recognize. Some of them I don't recognize, but for example, here is John Tenhundfeld. Here is Jake Keeney. Here is Hal Mendenhall. Here's Jerry Moore. Here is Buck Jordan. Here's John Mundy. And Harry Teeting. No, that's not Harry Teeting. That's Hubie Keck. That's Harry Teeting. And Joe Messenslager. And in back you can see the Heater 2 core and its erection dolly. The skin is on. And up here, of course, the control system.
We're fortunate today to have with us Charlie Schiltz, who worked for Frank Lynn during the Heater 3 days, the Heat Transfer Reactor Experiment number 3. And Charlie will go through that particular program, which was our final metallic reactor test that was done in Idaho. Charlie, welcome.
Thank you, Otto. Heat Transfer Reactor Experiment number 3 was the third in a series of 4 ground-based nuclear reactor tests leading ultimately to a flying model, which was going to look something like this. This shows the reactor in the center, flanked by 2 jet engines below and all the ductwork connecting the 2 of them. It was by far the most advanced test to that date, incorporating the latest developments and features consistent with an actual flying model. Its primary purpose was to evaluate and confirm performance characteristics of the reactor, which had been predicted largely by the analysis and non-nuclear testing. It was affectionately known in those days as Heater 3, which is a play on the letters HTRE-3. This power plant had the look and feel of a real flying system in terms of shape, size, weight. With the reactor positioned horizontally for the first time and 2 jet engines slung below, it almost looked like it could take off. Even into external structures, nuclear shielding and air ducting were representative of the real thing. However, a non-requirement of the experiment was the power and flow levels required to propel a large aircraft. Instead, these 2 parameters were set at relatively low fractions, such that maximum fuel element temperature and core discharge temperature would be consistent with those produced by much larger engines. This strategy allowed for proper testing of the 2 main threats without having to rely on yet unproven engine technology, and furthermore, by being the correct geometry, it would provide a base for extrapolation to higher power and flow levels later. The reactor itself incorporated innovative new design features which had never been tested before in both a nuclear environment and a horizontal attitude. Among these were the new solid, uncladded zirconium hydride moderators shown here. This is the leading edge, tailing edge, hexagonal shape, no cladding. It's just bare zirconium hydride. All previous tests had used circulating water as the moderating media, the mechanics of which were a spatial nightmare, always in the way of everything else. One only has to imagine pipes, manifolds, and headers competing for space where carefully balanced airflows were required, not to mention the risk of a pinhole leak, which would have destroyed the test. A very significant breakthrough was achieved in learning how to diffuse hydrogen into the metal to provide not only better moderation, but also a much improved capability for power shaping and flattening over monolithic water. Hexagonal in cross-section with a circular bore, as shown here, the moderators were equipped with longitudinal grooves around the perimeter, strategically placed for cooling by forced convection. Between the inner and the outer surface, between the inner surface and the fuel cartridge, an insulating sleeve was provided to limit both radiation and mixing from the fuel element channel. In the reactor experiment, several important design refinements were also incorporated in order to maximize exit air temperature while not exceeding allowable fuel element temperatures. Some of these included the following: a highly engineered inlet plenum designed to provide uniform air distribution over the face of the core. In this way, airflow could be more properly metered to each component by its own design. Second, the hydrogen content of the zirconium hydride moderators was ramped upward toward the outside for power flattening, towards the outside of the core. Power flattening in fuel elements was done by increasing UO2 content toward the outside rings. Fourth, heat flux at the tail end of each cartridge was increased by additional rings to compensate for a lower temperature differential between metal and air at that location. The moderators were extended well forward of the leading edge of the fuel cartridges in order to shift axial power peak forward, which was always the intent. The more you could get the power forward, the better the thermal performance would be. Sixth item, circumferential power scalloping around the reactor perimeter was trimmed with boron steel shims at the peak locations. Number seven, all of the variables associated with control rod worth in a brand new environment and with manufacturing or control system tolerances had to be systematically dealt with during the development of this experiment. And finally, while secondary nuclear heating in non-fuel components was not significant to overall system performance, it was clearly vital to their structural integrity. Calculation methods for internal heat generation, including Monte Carlo, were developed and used extensively for this purpose, and they are still being used today. Now for the reactor. The reactor had a nominal diameter of 51 inches with an active core length of 30.7 inches and an overall length of 43.5 inches. This is a view from the tail end showing the cross-section with some of the zirconium hydride moderators already hung in place. No fuel there yet. The core consisted of a hexagonal array of 151 moderator cells, each 4 inches across flats and with a 3-inch bore through the center. Surrounding the array was a beryllium reflector of varying thickness, filling the margin between the outermost moderator cells and the cylindrical pressure vessel, seen here. All components were supported from the front tube sheet, obtaining lateral-only support from the rear tube sheet. All axial thermal expansion was thus accommodated to the rear. Fuel cartridges, shown here, consisted of 19 stages of fuel elements. You see, and they looked something like this. This is a reduced size model which was used in a Heater 2 experiment. And then this was the same general geometry, only bigger in diameter, as you can see here. Each fuel element was composed of 12 or more concentric rings, each 1.5 inches long. The rings, shown here, were made from a blend of 80% nickel and 20% chromium, also known as nichrome, and fully enriched uranium, all cold pressed together, sintered, and the fuel matrix was then sandwiched between 2 layers of pure 80% nickel, 20% chrome cladding, and they were edge sealed by brazing. The composite was then rolled, hot pressed, roll formed into a ring, which is in turn brazed to the supporting hardware shown between the rings. While the design manufacturing process had been largely completed prior to Heater 3, and an enormous amount of work was done during this phase to minimize process variability and maximize performance reliability. Shielding consisted of lead steel and boral in this application, water-cooled for both simplicity and convenience. Having been designed to be airworthy and capable of supporting flight loads, the resources were just not spent on the design of an air cooling which would be needed for later for a flight prototype. Controls for the two engines consisted of two independent speed controls governing speed by throttling fuel flow. Once reactor air temperature increased sufficiently, fuel flow was gradually cut back and the engines were run at constant speed only. Later in the test series, a cold startup using the reactor motors, starter motors, and reactor heat only was successfully demonstrated, and we'll deal with that later. Reactor controls consisted of two primary independent but closely coupled systems. Reactor power was automatically controlled by the nuclear flux system, which in turn moved control rods in and out to maintain a set power level with an accuracy of plus or minus 1% over the full range. The temperature control system maintained a prescribed core discharge temperature by modulating airflow through a bypass valve in the external ducting. Backing up these two control systems were the safety systems monitoring temperature and flux levels at many strategic locations. The safety and control system loops were designed to be coincident type logic where 2 out of 3 circuits governed any safety action. However, the failure of any one of the 3 circuits would activate one of these safety modes. 1, the interlock mode, which prevented any increase in power demand, and 2, the override mode, which reduced power level, and 3, the scram mode, which caused immediate power shutdown. In addition, the scram event was designed to be completely independent of the control system, requiring only a signal releasing the spring-loaded rods to drive themselves into the core. Overall, the control system was fairly sophisticated for its day, but archaic by today's standards. How many times better it could have been with a fully integrated computer control system and better instrumentation. Now for the power plant. The turbo machinery consisted of 2 modified J47 engines, which were in current production at that time, with their combustion sections replaced by compressor discharge scrolls and turbine inlets fitted with special inlet annuluses. Each was equipped with a separate combustion chamber for full fuel operation. The reduced airflow for this application required the design of a brand new engine control system. Now, while the experimental hardware was being designed and built in Evendale, activities at the Idaho test site were at a feverish pitch. All kinds of remote handling equipment and skills were being developed for disassembly and possible reassembly of very hot components, nuclear hot. There had to exist a proven method for removing and replacing every last nut and bolt by non-human hands, a huge task. A platform had to be built, shown here, which could transport the test hardware from the assembly point to the test site, make all the necessary connections, manage the test, and finally return the system to the hot cell for disassembly and evaluation. A major accomplishment was the construction of the test dolly, whose weight and span was supported by 4 railroad tracks. A rough idea of the amount of hardware involved in this test rig was given by the total loaded weight of almost 270 tons. I remember one of our competitors took that picture and put a caption under it, "This is supposed to fly," or something like that. You remember that? Okay, now on to the test. After assembly, the reactor was tested at very low power levels between April and June of 1958 in order to confirm nuclear design parameters and to provide basic data for the as-built system. During the series, the reactor poison profile was altered 4 times to achieve the desired flatness of the radial profile. On September 8, 1958, the assembled experiment was finally wheeled out to the initial engine test facility, known as the IET, for shakedown run of the overall power plant. During this period, a number of adjustments were made to operating profiles, again, due to differences in performances at elevated temperature. Unexpectedly, a power excursion occurred during these tests, which resulted in the overtemperature and collapsing of fuel element rings. The positively identified cause of this problem was an erroneous reactor power indication during the withdrawal of control rods. It was a false signal. The false signal was associated with a high series resistant noise filter in the output of each ion chamber's power supply. It had nothing to do with the instrument itself, but it had to do with its power supply. The overtemperature condition appeared to have happened so fast that some melting of fuel elements occurred before the automatic scram function took place. Immediately following this failure, the system was returned to the hot shop for disassembly. Except for the fuel elements, no significant damage was found in either the reactor or the rest of the power plant. However, a 6-month delay was inevitable before testing could be resumed. On June 8, 1959, the refueled core was returned for low power testing again and was found to duplicate the system parameters of the initial core within specified parameters. Following a minor alteration of the poison configuration, the reactor was returned to the IET on July 28, 1959, and went critical on October 9th of that same year. The reactor was brought to a power level of 10 megawatts and controlled stepwise increments with thermal and nuclear measurements made at every step. After completion of this series, the plant was examined for defects in the hot cell. None were found. The analysis of test data verified that performance had met or exceeded all expectations under these test conditions, and the system was now ready for full power testing. On December 14th, 1959, the plant was wheeled out to the IET for endurance testing and was successfully operated for 166.5 hours at very low power levels. Then the reactor was brought to full power in 6 incremental steps, ultimately reaching 31.8 megawatts. During this series, data was gained on the relative contributions of chemical versus nuclear energy to the engine performance. With this data now available, 6 transfers to full nuclear power made. Further testing was done over a wide range of engine speeds and nuclear power levels. Startup and cool down transients were also studied. Probably the least trivial accomplishment of all during this series was the accumulation of 126 hours of endurance at full power, including one run of almost 65 hours. The icing on the cake was, on disassembly, finding all components in excellent condition and ready to run again. However, the most valuable product of these tests is found in the mountain of information and tons of operating data, all of it worth its weight in gold to the engineers and scientists who only a short time before had only theories and calculations to go by. Well, Heater 3 lay dormant for about 10 months when it was again wheeled out for a special test to verify the power plant could be started on nuclear power alone instead of having to start on combustion and then switching to nuclear. This was an extraordinary tricky assignment, requiring the simultaneous management of a large number of variables, all in the transient mode. While an analog simulation model was constructed, only a human being in those days could be trusted to watch all the gauges and move all the dials exactly the right time and the right amount. A very proficient operator was found, and he did it not just once, but 3 times in December of 1960. A post-test analysis revealed that manually controlled transients closely followed the simulation model. And this feat is approximately the equivalent of manually piloting a modern aircraft that can only be flown by wire. It's that difficult. Between the second and the third nuclear startups of that previous test series, the reactor was operated at 29 megawatt for 1 hour. Then it was manually scrammed to simulate an uncontrolled shutdown. In the absence of turbojet airflow, this condition might have resulted in serious consequences, including overtemperature of some components. But with one blower furnishing a modest amount of aftercooling air, all measured temperatures declined steadily and relatively uniformly, with no damage resulting. Finally, an elevated temperature test was performed to determine system integrity under a temporary worst-case scenario where maximum fuel temperature was forced to run at or near 2,030 degrees Fahrenheit. The test lasted 20.3 hours, with all other parameters remaining stable and a clear indication that normal operation could have been resumed. All testing was thereby concluded, leaving a lasting impression that nuclear-powered flight was indeed possible. The HTRE-3 program had clearly met or exceeded all of its technical objectives. But much more significant was the confirmation that dedicated, hardworking, intelligent people could transpose an idea from the depths of unknown knowledge to a real working apparatus. Some of the key players in the design of the reactor, including the following: Frank Lynn, who was the program manager; Bruno Bonini, who I believe was materials and procurement manager; Jack Simpson, supervisor of thermonuclear analysis; Aubrey Smith was principal engineer of mechanical design; Henry Bermanis, also known as Hank Bermanis, thermonuclear analysis; Mike Goldstein, nuclear analysis; Fred Robertshaw, our materials expert; Ray Cook, who did all the design work on the fuel and the moderator; John Mundy, our manufacturing engineering specialist; Charles Jones, who did reactor component design; Roy Eckert did reflector design; Aaron Spivak handled some of our stress analysis; Jack Cole, also stress analysis; Bill Chenault, who was responsible for some of the core hardware items. These are only some of the key players associated with the core design. Many, many more people made major contributions to the power plant and its testing, and here are a few of them. Many of those faces I don't recognize, some I do. In the fullest of time, of course, nuclear powered flight was not destined to become a reality. But that does little to diminish the success of Heater 3 experiment. And for the rest of their lives, the men and women who made it happen believed that it would have succeeded. And along with that goes a legacy of pride and satisfaction and confidence not commonly shared by everyone.
If anybody were to ask you what the most important aspect of the ANP program was, the answer would come back: materials, 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 materials. And one of the most important feature of materials was, what materials do you use? What materials are acceptable in nuclear reactors? Long before ANP got started, in the days of the atomic bomb development, an intense program was conducted at the Brookhaven National Laboratory to measure what is called cross-sections of nuclear materials. These cross-sections essentially involve the impingement of a beam of neutrons of various energies on the material itself. And the objective was to measure what the absorption was of the neutrons, what the scattering characteristic of the neutron, in the case of uranium and other fissionable materials, what the fission cross-section was. And from that information, the materials scientists were able to determine the kinds of materials they wanted to use in the reactor. In some cases, you want, for a control rod, you want a material that absorbs neutrons. In the case of a reflector, you want a material that's going to not absorb neutrons but bounce them back into the core. And of course, in the case of materials you're using for structures, like aluminum or stainless steel, you want the material not to absorb thermal neutrons so that they are available ultimately for the fission process. These measurements were compiled in a book that looks like this. It was available at ANP, and in essence, it's a compilation of the cross-sections of all the materials and their various isotopes that were available at the time. In the case of like a control rod, there are several materials that were looked at. You look through the book, for example, and you can see what a cross-section for boron is. Boron being looked at because it has a very high absorption cross-section. You can see it starts out over here at the higher energies at about 15 or 6, no, at about 6 or 7 barns. Barn being the measure of the cross-sectional characteristic of the material. And as the energy of the neutron slows down, you move over here, and you get up into the neighborhood of 3,000 or 4,000 barns, which by comparison to other materials indicates that boron is a very good absorber. Oh, there are even better absorbers for neutrons. For instance, europium, a rare earth, looks something like this. You get down into the thermal neutron region over in here, and you're up in the neighborhood of europium, happens to be on this page. You're up in the region of, down in here in the thermal neutron region, you're up in the neighborhood of 30,000 barns. Compare that to 2,000 or 3,000 for boron. It makes europium look like an excellent control rod material. The question is availability and cost. In the A&P reactors, we more or less defer to the cheaper material, boron. So from the standpoint of what went into a reactor, this particular set of information became more or less a Bible. You consulted this every time you wanted to incorporate a new material or a different type of material in the reactor core to see what its effect on thermal neutrons was going to be.
While the heat transfer reactor experiments were being designed and fabricated and developed for further work and then tested in Idaho, advanced engineering and the A&P laboratories were diligently working to identify the power plant that should fly. The mission, however, proved to be a moving target. We have Tom Hunter with us today, who was a member of this advanced engineering team. Tom, welcome aboard.
Thanks, Otto. Well, you're right. It was a moving target. I'll try to put it in context for you here if I can today. The General Electric Company, based on its experience in the development of turbojet engines, took on the task of developing a nuclear power plant for a manned aircraft. The system that would be utilized by GE was referred to as the direct cycle. By that, the direct cycle means that the air from the compressor of the turbo machinery was passed directly through the reactor where it was heated, and then into the turbine and into the nozzle, and thereby providing the necessary thrust to meet the mission requirement. Pratt & Whitney then was asked to look into an indirect cycle. Now, the indirect cycle essentially took the heat from the reactor, transferred it into a liquid metal circulating loop. This loop then went through an intermediate heat exchanger where a secondary loop of liquid metal was discharged in a radiator into the center of the turbo machinery. And in the same manner then, the compressor discharge air was heated by the radiator, went to the turbine, out the nozzle, and provided the necessary thrust. These early years, the 1951 and 1955, were primarily research and development, R&D. The unknowns were many disciplines that had never been explored before. Nuclear radiation problems had to be combined with thermodynamics, structural problems, shielding problems, reflectors. All these were new materials to the A&P program. The shielding had to be such that it could protect the crew and the aircraft parts from radiation damage. Design studies of various configurations were prepared in order to develop the concept. As a mission, the general concept was to provide extended range and endurance on nuclear power alone at medium altitude, high subsonic speed, with chemical augmentation to give a dash of Mach 2.5 at 65,000 feet. This generalization provided an early guideline in the R&D program. The early work, however, gave an indication of the difficulty in obtaining the necessary temperatures to provide sufficient thrust. Also, shields had become quite heavy to provide the necessary protection for the crew. Studies on how to maintain the system from a remote handling standpoint also proved to be more difficult than we had imagined. The general arrangement to optimize these problems led to the utilization of a single reactor with 2 turbojet engines, one on each side of the reactor. This became known as the XMA-1A series. 2 of these systems were necessary to provide the proper propulsion power for one aircraft. This meant that 2 of these would result in a flight weight of approximately 500,000 to 600,000 pounds for the aircraft. Now, this seemed to be pretty large and pretty heavy in those time period. But if today, it's not unusual to find a C-5A or an extended range 747 approaching 1 million pounds in gross takeoff weight. By 1955, the Air Force, the DoD, the AEC all felt that it was necessary to focus the effort towards nuclear flight. Accordingly, the 125A weapons system requirement was established. This operational requirement was referred to as number 81, and it called for a cruise-cruise mission. That was specifically to provide cruise on subsonic on nuclear alone, with the dash at high altitude, supersonic, utilizing the nuclear plus chemical fuel. This was the first hard objective put on the program. Ballistic missiles were under development. In-flight refueling of bombers was being developed. These events were making it necessary to establish some definite goals for the nuclear-powered aircraft. However, there were still many problems to be solved. There were limitations on available materials to meet the high temperatures. This resulted in a reduction in the predicted performance. The dash radius was less than required. Shield weights had increased. However, there were many accomplishments in this same time period. The HTRE experiments, the Heat Transfer Reactor Experiments, provided many accomplishments as their testing was accomplished at the Idaho testing station, where they were evaluating new materials. These included metallic and ceramic fuel elements, coatings, moderators, reflectors, all these leading to obtaining higher temperatures. The heater tests obtained the necessary airflow for testing by operating the attached turbojets on nuclear power, and could also operate on chemical power. During the entire heater series, many hundreds of hours were run on nuclear power alone. The large X211 turbojet engine, designed to match the reactor, was being developed at Aircraft Engine Group. Convair was under contract to modify a B-36 bomber. It would now be designated the X-6. This was to be used for flight tests to evaluate the divided shield concept. A reactor of low power was installed in the aft bomb bay, while a separate crew shield was provided in the forward part around the crew compartment. The reactor of low power was operated in flight. About 40 flights were made, with 24 of those being with the reactor operating, to measure the effect on the crew compartment and to evaluate the activity on the various aircraft components. Also, valuable experience was gained by studying the remote handling problems of the radioactive reactor system. However, the problems of meeting the 125A mission resulted in redirection of the program back to an R&D effort. There was still a strong interest in the extended range aircraft, but the ballistic missiles and the in-flight refueling systems were moving ahead, and accordingly it was necessary for increase the performance of the nuclear power plant to be competitive with these other systems. Accordingly, work was directed toward materials which would provide higher temperatures. At the same time, there was conflicting directions as to the next goal. Some wanted an early flight with a prototype. Others wanted to wait until a definite mission objective could be established. The Strategic Air Command, SAC, proposed an operational requirement for a CAML mission. CAML stood for Continuously Airborne Missile Launcher and Low-Level Weapons System. This CAML mission had these specifics. It was to cruise at 30,000 feet at Mach 0.9. It was also to have capability to fly on the deck at Mach 0.9, which is more difficult than flying 9 at altitude. Convair won a contract against Lockheed to work with General Electric on the initial design of a nuclear-powered manned bomber to meet the CAML mission. There was no airplane development program authorized at that time. The prospects in 1959. General Electric was satisfied with the requirements of the CAML mission and worked with Convair on design studies based on utilizing the XMA-1A metallic fuel element early, with later use of the XMA-1C with the ceramic fuel element. GE proposed that the aircraft check out be on chemical fuel only, with the first flight being made on the XMA-1A and next flight being made on the XMA-1C with the ceramic elements. R&D efforts should be pressed ahead to develop higher temperature fuel elements in order to get higher performance. The XMA-1A resulted in turbine inlet temperatures of about 1,500 degrees, while the XMA-1C with the ceramic elements were able to provide T4 turbine inlet temperatures of 17 to 1,800 degrees F. By August 1959, the XMA-1C, XMA-1A had been canceled as not being able to meet the requirement, which was now asking for longer life and increased performance. In February 1960, Convair and GE completed a study of propulsion systems evaluating the two-engine, one-reactor, the XMA-1A series, as opposed to the single-engine, one-reactor system. GE recommended the single engine and now designated it as the P-140. Several configurations were studied. A symmetrical design with the compressor shaft going right straight through the center of the reactor core to the turbine. This symmetry made for a simplicity of design relative to structural requirements. A second version was looked at where the reactor was pulled away where it could be shielded more effectively, but this then required the compressor air to be ducted into the reactor and then back out of the reactor and into the turbine and out through the nozzle. A third configuration took another look again at what we call the twin engine, the two engines on one reactor. This is similar to the XMA-1A series. But when we took this into an aircraft installation, we had to have two of these, which meant we had a very broad power plant installation problem. The chosen design was the shaft to the center of the core. This arrangement, similar here in this mock-up, shows the inlet with the compressor discharging through the reactor, through a combustor, and into the turbine, into the nozzle. The power plant could be run on chemical alone, using the combustor, the chemical combustor, or nuclear alone, or a combination of both. This symmetrical design, then, was the chosen design. So what could we do with the aircraft? GE had chosen the P-140. I want the model. Convair came up with an aircraft which they called the NX-2. The NX-2 is a canard configuration. By canard, it means that there's no tail feathers, no stabilizer and rudder. There is a small elevator in the front. This concept was quite effective for a divided shield concept, in that the power plants then could be mounted as far aft as possible with the crew as far forward as possible, giving the greatest separation between the power plant, the reactor, and the crew. This also has the advantage of being able to put the three engines together. Next one. As you can see in this configuration drawing, the three engines are mounted side by side. We refer to this as being Siamese. It has a definite advantage, in addition to being far separated from the crew. Next one. It has the advantage of doing shield sharing. Now, by shield sharing, this simply means that if you look at the end view of the power plant, we could lop off the side shield on the center power plant and the inboard side of the external power plant, so that this shield was sharing here and this one here. This resulted in a net savings in the shield weight. Okay. In order to get the true evaluation then, the combined studies were based on these kind of requirements for the NX flight. A Mach 0.8 at 35,000 feet with a minimum thrust of 8,120 pounds, with an engine life of 1,000 hours, with a turbine inlet temperature of 1,800 degrees F. This set of requirements then was transposed into a typical mission for the NX-2 weapon system. This flight profile, this being the runway, shows that the aircraft would take off on chemical fuel alone. On the climb, it would switch over to nuclear fuel and continue its climb on just nuclear power until it reached its on station here at Mach 0.8, 35,000 feet, whereby if it were required to make a penetration, it could make a penetration at altitude or on the deck. If not, it would continue to orbit on station for approximately 120 hours. At the end of that time, it would then return to base, where it would transition back from nuclear power to chemical power and would make the landing under chemical power. Thereby, both the takeoff and the landing were under chemical power, thereby minimizing the radiation effect on the flight station. The last chart, pretty complicated, but it shows the degree to which these studies were made, where we looked at the different flight profiles, the ground checkout, the chemical takeoff, the climb to station, the cruise on station, the mission on maneuver on station, the two-engine operation, and so forth. These parameters were all studied to evaluate the concept of the NX-2 with the P-140 engine. Typically, at the on-station flight profile here of 0.8 at 35,000 feet, the thrust developed by each power plant was 8,120 pounds. At the time, it was using a turbine inlet temperature of 1,740 degrees F. Take it down. These design studies, for the first time, indicated that a P-140 power plant in the NX-2 aircraft could meet the requirements of the CAMO mission. Development of the ceramic fuel elements was progressing very satisfactorily. The NX-2 aircraft was ideally suited for a prototype test bed. However, the program was canceled in 1961 after finally achieving what was considered to be a prototype configuration that had reasonable possibility of being successful as a manned nuclear-powered aircraft.
Hi, Garth. Good to see you again.
Nice to see you, Otto.
In 1955, the major decision was made to build the X211 engine, and also to have the twin engines for one reactor. Could you give us some background on that?
As I remember, Otto, the single engine design was proposed in early 55, possibly late 54, and not too much work had been done on it compared to the twin engine version, which had been studied for a long while. There was a study put together to compare the performance of the single engine configuration and the twin engine configuration. And I might mention as a preamble that it was going to be a turbojet. We wanted potentially supersonic flight, and there were no fan jets in existence at the time, and of course propellers wouldn't give us that speed. The comparison study lasted for several weeks, as I remember, and Wally Thompson suggested we use a 10-point must system as the fighters use. In other words, whatever parameter you were comparing, you give it 10 points, And if for example, the twin engine had a lower weight than the single engine, then the twin engine would get 10 points, and the single engine 9 or 8 or 7, whatever you thought. So there was a fair amount of judgment in this comparison. On the other hand, we had not enough engineering data to do a detailed comparison in terms of all the parameters you're interested in. The primary one, of course, was the thrust to weight of the engine. The reactors themselves were not that different. The major difference, of course, was the single engine had the shaft through the core. The twin engine system had very long shafts outside the core, as well as a complicated ducting system. Many of the arguments relating to the comparison involved parameters that were difficult to quantify or even measure in any way, like which one is going to be easier to build, easier to repair, easier to maintain, that question. The end result of the study was, as I remember it, the twin engine configuration was selected as the major configuration to proceed with.
Now there was another, besides the shaft through the core for the single engine, there was another one where the reactor was ahead of the engine. And it was a twin, but there were two engines and the reactor was up in front. And Jack Hope had...
I don't remember that particular configuration, so
It may have been discarded prior to this decision.
Yeah, the one we were actually studying in some detail was simply the one that became the XMA one, the twin engine with a reactor and the two engines on each side.
Right, right. And this is before we tested even the first reactor, the metallic heater 1.
Before that test, yes.
Because that was in January of 56.
Right.
Mm-hmm. Well, thanks, Garth.
Okay, I can't think of anything else to say about it at this point.
That covers it.
"41 years ago, the Air Force proposed the 125A weapons system with the following objectives for the aircraft: continuous cruise for 40 hours on nuclear power at Mach 9/10 above 20,000 feet, and sprint near the target area for 2,000 miles at Mach 2.5 and 55,000 foot altitude, including a low-level penetration at Mach 9/10 on the deck, that is about 500 feet. The turbomachinery designated for this was called the X211 and was placed under development in the large engine department of General Electric in Cincinnati. We're pleased to have with us Bob Miller, who was the mechanical systems engineer on this X211 project. Welcome, Bob.
Thank you, Otto. I'd like to describe the turbomachinery program to you today. I'll use two charts and then several photographs that will actually show some of the hardware that was used in the program. Now, on the first chart, you can see there were two configurations for the X211. The first was called the twin because there were two sets of turbomachinery operating on a single core reactor. This was done because it was not feasible at that time to run a shaft directly through the core. Later on, with a new reactor, it was determined that they could run a shaft directly through the core, so then we came up with the inline version. The program was initiated with a task force in June of 1955. And then followed the design and manufacture of the hardware, with the first engine to test for the twin in January of 1958. The first engine, however, was a single active engine on one side with a dummy on the other side for the first operation. The first real twin with two active engines was in January of 1960. The first engine to test was in January of 1958. That was the twin configuration, but only one side of the engine was active. The other side was a dummy simply to represent the weight and inertia of a set of turbomachinery. The first twin operation was in January of 1960. The first of the inline engines ran in December of 1959. And we'll see some of this turbomachinery later on. The program was terminated, unfortunately, in March of 1961. This next chart shows some of the design parameters for the engine, in that the airflow was 425 pounds per second per set of turbomachinery, which means that the twin engine core was operating at 850 pounds per second. The turbine inlet temperature at military power was 1700 degrees Fahrenheit, and that was to be increased slightly to about 1800 degrees for the inline version. The max thrust was achieved at 27,370 pounds, and at that time, that was the highest thrust achieved on a turbojet engine. Now, as you will see in more detail later, these two configurations required quite different combustion systems. The twin engine required parallel combustors running around the outside of the reactor. However, in the inline version, combustors were built in behind the reactor core. We tested 6 of the twin engine configurations and 4 of the inline configurations for a total of 758 total test hours. I don't have the detail to split that down. I'd like to remind you now of some of the management people involved in the program. Bruno Bruckmann was the manager of the engine program, and he is here shown discussing the 1/10 scale model of the twin configuration with Roy Schultz, Herman Miller, and Don Berkey. It was hard from that picture to get a real sense of the size of the X211 turbomachinery. So this picture shows a comparison of the X211 1/10 scale model and the J79 1/10 scale model. The J79 was 207 inches in length with a 34-inch diameter compressor. The X211 has a 54-inch diameter compressor and a 510-inch length. And 510 inches is 42.5 feet, which gives you some idea of the size of the engine. Of course, while the engine design and manufacturing was in process, it was necessary to build a new test cell. This was built at the Evendale plant in the back of Building 500, and here you see the test cell with the inlet air duct and the air discharge duct. Now I'd like to talk about the actual turbomachinery a little bit. This picture shows the simulated core used for the turbomachinery development. The core assembly has in the front of it a valve which is used to control the pressure drop and also to shut off the core flow when it's necessary to operate on the parallel chemical combustors. This next picture shows the core assembly from the back. So you can see the burners, the chemical burners that were used to simulate the reactor heat addition. Also, this picture shows the bearing supports for the shafts which ran on each side of the core assembly. This picture shows the engine in the assembly area, which gives a much better visualization of the overall size of the twin configuration. You see there's one engine here with a dummy, in this case, on the left side. And we see here the 16-stage compressor with its variable stator mechanism. And then there's the collector and the reactor simulator or core, the turbine collector, turbine inlet collector, and the three-stage turbine, the exhaust pipe, and jet nozzle. The chemical parallel combustors have not yet been installed at this particular point. This is a similar shot, except this time from the aft looking forward, so that you can see the variable exhaust nozzle, the exhaust pipe, and again the collectors and the combustors and the compressor in the distance. This picture shows the twin configuration being rolled into the test cell, being pushed by the dolly that you see in the front. Off to the side, we have a compressor inlet screen which is rolled in front of the engine to prevent foreign objects from going through the engine. Anything that might be loose or break loose from the cell during the actual operation. This picture shows the first of the inline engines that's assembled. And so you see again the compressor and simply a frame going from the compressor to the core, and the same core as we had before, perhaps slightly modified, and a frame going to the turbine, the three-stage turbine, the exhaust duct, and the variable jet nozzle. And you can see that it's greatly simplified because we have been able to eliminate the two collectors, the compressor collector and the combustor discharge collector or turbine collector. And these were the two most complex pieces of equipment that were required in the twin configuration. And of course we were happy to be rid of those. This last shot of the turbo machinery shows an inline engine in the test cell with the inlet screen in position and with the test equipment starter connected to drive and start the engine. In the final version, the starter would be an air turbine starter which would be built into the compressor bullet nose. This last picture shows a group of the management people on the program standing in the exhaust collector of the test cell. You may not be able to recognize these people, but I'd like to point out just a few. There's Gerhard Newman and Bruno Bruckmann and Stu Beekman and Jim Harrison, who was the engine test manager, and several others that I won't introduce at this point. Now, this is the 1/10 scale model of the X211 twin configuration. It doesn't look very large from here, but recognize this man and the fact that this compressor rotor tip diameter is 54¼ inches, and the overall length of the engine is 510 inches or 42½ feet. Now let's go quickly through the twin configuration. There are two sets of turbo machinery, obviously. working through a single reactor. Each set of turbomachinery consists of a 16-stage axial flow compressor with variable vanes. In the final version, there were 6 sets of variable vanes, but in the initial test configuration, all stages were variable in order to establish the aerodynamic performance of the compressor. The compressors then feed into a compressor collector, and the 2 compressor discharges are gathered together and fed through the single reactor core. Now we'll come back later and talk about the chemical burners which are on the outside, and you can see there are 3 ducts taken off of the compressor collector. Those are split each into 2, so we have 6 chemical burners which bypass the reactor core. These chemical burners are necessary for starting and for operation on chemical for takeoff and so on. The core and the chemical burners discharge into the turbine collector. Now, the fact that we have a twin configuration introduces some complications into the turbomachinery, namely these collectors, which are a complex pressure shell, as you can imagine, and particularly this turbine collector required internal insulation to provide a shell that was cool enough to have adequate strength to support the turbines. Also, the size, the spacing of the compressors and the turbomachinery is determined by the size of the reactor, because the drive shaft for the compressor from the turbine runs right along as close as we could to the reactor.
So the shaft is on the outside.
The shaft is definitely on the outside of the core. That's on.
Outside of the shielding too.
Well, I don't know if it's outside of all of the shielding, but it is outside of some of it anyway. Now, for factory test purposes, we built a chemical burner inside of a simulated reactor so that we could operate on the reactor simulated by the chemical burners, or we could operate on the parallel chemical system. Now, in order to do that, you also had to be able to operate either engine independently, this one or this one. So that meant, say, if you wanted to operate that engine, you had to shut off this compressor so the airflow couldn't backflow out through the second compressor. And similarly, you had to prevent flow from going out through the turbines, so that it was necessary to establish several different valves throughout the engine in order to make operation possible. Also, there were valves in the combustor air inlet ducts in order to shut those off, so then you could operate through the core system. Also, you can see the bullet nose where we had the bevel gear drive that drove the accessories, which were located down on the bottom, and the starter motors on the outside, as you can see here. The aerodynamic and mechanical design of the basic turbomachinery was based on the J79, which was a contemporary in the design phase of this X211 turbomachinery. But of course, the J79 compressor inlet diameter was like 29 inches, something of that order. There's a picture here that we perhaps should have mentioned earlier, but it gives a quick overview of a typical turbojet, really. It has a simple axial flow compressor with a heat source, which may be a heat exchanger in this case, and core reactor, or it could be simple chemical burners as it is in a normal jet engine, then the turbine and exhaust. So that's the basic system. You can see the variable stators in through here, and this was the actuation system. And primarily you can see better the combustor arrangement for the bypass or parallel flow system. Fuel nozzles were located here for each burner, and valves here, so each of these systems could be shut off when you were operating on the reactor. There are 6 chemical burners, internal liners here to provide for the combustion, flowing into the turbine collector, through the 3-stage turbine, and into the exhaust, and perhaps you can see the variable jet nozzle here. Initially, it was simply a conical nozzle, but in the later versions, it was going to be a conical convergent divergent nozzle. But we never actually got that far. The engine was mounted from the reactor. Of course, the reactor was mounted from 3 points, apparently here, and two back here. But all of the turbomachinery components were suspended from the reactor.
Objective of the X211 project at General Electric Evendale is the design, development, manufacture, evaluation, and supply of turbomachinery for aircraft nuclear power plants. The immediate objective is the development of turbomachinery for an advanced reactor core test program. A further objective is the continuation of a program of engineering study, design, and component testing for flight and use with reactors having substantially improved performance. The X211 engine being developed for the advanced core test is an inline shaft-through reactor direct cycle engine with an overall length of approximately 37 feet and inlet diameter of 54 1/4 inches. The military thrust is 23,900 pounds without afterburner. The engine, which you will see in the following sequences, is a Z configuration. The Z engine is built up of parts developed for a former twin-engine configuration, modified as necessary to adapt to the single inline configuration. The Z engine is a test stepping stone between the twin and the engine being developed for advanced core testing at Idaho. In this diagram, the center section containing the reactor has been omitted because of security restrictions. The compressor has a 12.6:1 compression ratio and airflow of 425 pounds per second. The compressor stator vanes are being machined while assembled in the casing in order to gain optimum concentricity of the vane tips with respect to the rotor. The engine parts are thoroughly inspected prior to assembly. The compressor rotor is turned over slowly while the inspector receives an accurate reading of the tip radii in order to ascertain being within print tolerance. Eccentricity of rotor parts is also checked in this fixture. Blades in all 16 stages of the rotor have been instrumented with strain gauges in order to assure optimum use of engine hardware and test time in the cell. Let us look closer at an instrumented disc. In this case, a disc to be used in a component spin test. Lead wires are carefully nichromed to the surface of the disc. Wires in engine testing are let out the front end of the engine where the strain gauge signal is taken out through the slip ring. The strain gauge signal is read on an oscilloscope. The compressor front frame contains the inlet guide vanes which can be controlled as to angle. All 16 stages of compressor stator vanes are also variable. In order to assure a proper design to withstand the forces encountered in later service, the inlet guide vanes are subjected to hailstone tests. An ice ball of standard size is enclosed in plastic and inserted into the air gun. The vane is placed into the fixture, and the gun fires the ice ball at a velocity of approximately 490 miles per hour, while a high-speed camera photographs the effects of the ice ball on the vane. The results are analyzed, and tests such as these lead to design of optimum strength, weight, and reliability throughout the engine. In the subassembly area, where the compressor front and rear frames and stator casings are mated to the compressor section, some of the details of compressor construction can be seen, such as the 16 stages. Notice the large movement of vane possible by this unique design. Notice also the shrouds on the early stages of vanes. On the engine, the vane movement is checked out prior to using the engine in the test cell. The X211 engine can be capable of both nuclear and chemical operation. The use of a test rig is being employed to develop an optimum burner for chemical operation of the engine. Testing continues into the night. The turbine shaft passes through the center of the reactor and as such is exposed to high temperatures. The shaft is air-cooled. The X211 turbine shaft of approximately 17 feet is extruded by a subcontractor. Many machining operations, preparations are being made to balance the turbine shaft prior to installation on the engine. The three-stage turbine rotor is balanced by optimum distribution of the blading at assembly and then final balanced by balance washers at the last stage disc. Turbine front frame of welded A286 is lowered gently onto a fixture prior to the casing assembly. Stator rubbing strips are assembled into place. tied to the bolts. Remote handling equipment will be a necessity in assembling some of the components in the later phases of testing at the Idaho test site. The turbine casing remote handling development program is shown here in its initial phase. To ensure successful operation of controls and accessory components under severe conditions, continual development testing is run on this test rig. Careful planning, programming, and procurement of hardware and assembly, the engine is ready to go to test in cell X1 in the large jet engine department. The present engine testing is accomplished with a chemical test burner, simulating a reactor to permit independent development of the turbo machinery. Air resistance simulating the reactor is accomplished by varying the inlet area through the porous plates shown. Combustion is accomplished in the 19 burner cans. The assembled engine is rolled on the dolly into the cell where final instrumentation will be accomplished. Notice the length of the Z engine, approximately 42 feet. Incidentally, the Z engine has already developed on test stand at Evendale the highest net dry thrust of any jet engine in General Electric history and has exceeded thrust requirements for the Advanced Core test engine. Large number of instrumentation wires leading from the engine are to ensure maximum utilization of test time and to protect the engine in the development phase of testing. The engine starter used here is a 500 horsepower steam turbine, later to be replaced by a prototype air starter. The variable area jet nozzle is checked out to make sure of proper functioning prior to firing. Last-minute checking on the engine is accomplished. Testing is underway, with all members of the evaluation and test teams at their stations. Data is gathered to verify pre-test predictions by systems analysis. Testing of the X211 engine continues, directed toward achieving nuclear flight in planes of this type being designed by Convair, the NX-2. Achievement of aircraft nuclear flight will open an entirely new era in aviation.
I want to talk today about the XMA-1A reactor, but I think I should start by giving you a brief overview of the total XMA-1 power plant, including the X211. This first chart shows the overall power plant. The XMA power plant was a nuclear turbojet system designed to operate on both chemical and nuclear fuel. It consisted of a single reactor shield assembly, shown here in black, and two turbojet engines with the center section taken out to make room for the reactor. I wanted to start out first talking about some of the significant differences between the HTRE number 3 and the XMA-1A power plant. Just to refresh your memory, the HTRE stood for the Heat Transfer Reactor Experiment number 3, and it was generally referred to as Heater 3. Heater 3 had 19 fuel elements, which were 1.5 inches long, whereas the XMA-1 power plant had only 9 segments, but they were 3 inches long. This additional length was introduced to improve the aerodynamic flow through the engine and the heat transfer from the reactor. The moderator for the both of these was zirconium hydride. The difference being that in the Heater 3 array, the fuel elements were pushed down the center of a solid zirconium hydride bar, whereas in the XMA-1A, the fuel element was integral in itself, and a tri-fluted arrangement of moderator was provided around the fuel element. Both the reflectors were beryllium, and the shield in the Heater 3 was lead and water, whereas the XMA-1A, since it was to be a flight type version, we had to get rid of the water, and we went to borated beryllium and tungsten in the front shield, lithium hydride in the side shields, and borated beryllium oxide in the rear shield. This shows a somewhat exploded view of the reactor itself. And these elements are pulled out of the shell. This would be the reactor itself, and the part that we saw that was in black on the initial picture. The first thing that's inside there is the core. And then in order to contain the radiation of the reactor core, it had the side shield around it, a rear plug came in from the rear, a front plug came in from the front, and this is the bypass valve, which I talked about before. In addition, the side shield was not complete because it ran in the way of the engine shafting, so there was a bearing support beam on both sides which completed the shield and provided support for the turbo machinery shafting. The bypass valve, as shown in this chart, was located at the front end of the shield, and its function was to cut the air off through the reactor when the engine was running on chemical fuel. In other words, it was going through those side pipes. The valve consisted of a nose section in which there were cylinders put down through it, and in each of the areas where the air flowed, this cylinder had a hole through it, so that when it was shut off, it was twisted in this direction and the air ran into a blank wall, so to speak. When they wanted to open it up, that was turned 90 degrees and it presented holes where the face was, and that allowed full flow through the reactor. This type of design allowed for a very low pressure drop across the valve when it was in its open position. The valve was supported at the front, shielded through connections in the nose caps and the wavy walls, and 4 splines on the valve flange ring that engaged matching fittings in the front flange. The bypass valve was actuated by a push-pull linkage system. 2 sets of levers, one at the top and one at the bottom, provided the required motion for the blocking cylinders. And they were connected from an actuator cylinder through a linkage mechanism, one of them being located on the bottom and one of them being located on the top. Okay. The XMA reactor core was a cylindrical assembly 62 inches in diameter, 38 inches long, and these dimensions encompass both the side reflector and the forward and aft reflectors. The core consisted of 151 holes for fuel elements, and those were within cartridges in a matrix of unclad zirconium hydride moderator bars. In addition, there were to the 151 fuel holes, there were 129 other holes that went clear through the reactor, and these provided the paths for the control rods, there being 129 of the control rods. And it also provided a structural connection between the front and the rear of the reactor core. This design permitted the air leaving the compressor to pass through the full length of the core in a single pass to cool the core components and pick up the reactor heat. This chart here shows a summary of the reactor core. 38 inches in length, 61.9 inches long. It weighed 11,900 pounds. It had 151 fuel elements in it, which were spaced at a 4.387 center-to-center distance. It also had 129 control rods. Now, of the 129 control rods, 122 of those were what we called shim rods, and 7 were called dynamic rods. In a typical operation of the reactor, the shim rods would be pulled out until the reactor went critical or achieved the required level of power. Say it was 25% power or 50% power. And these rods would be pulled out until that power level was reached. At the same time, the 7 dynamic rods were more or less positioned in their central position, so that the shim rods established the power level and the dynamic rods took care of minor variations around that power level. Now, the shim rods would have to be pulled out various distance, depending on the age of the reactor, the time since shutdown, the temperature of the reactor, so that it had could travel the entire 20 inches, and it may start out early in its life, maybe 4 or 5 inches retracted, and towards the end of the life of the reactor's life, it would be they would be almost fully retracted. This is a chart of the XMA-1 fuel cartridge, and that consisted of 9 3-inch segments of the fuel elements, which were somewhat similar to this fuel element here. This happens to be a 1.5-inch fuel element, but they were similar to this with the exception that in the XMA-1 there was a large hole down the center of the fuel element for a moderator bar to be put inside. That was one of the things that was learned in some of the earlier experiments, that we needed moderator inside the fuel element bar. The center moderator bar was mounted in the center of the assembly. The outside surfaces of the fuel element was covered with a fairly thin insulating material to minimize the heat from the fuel elements into the moderator and to keep the moderator at a reasonable temperature. The fuel cartridges were designed so they could be remotely inserted and removed from the rear of the core. A fuel latch in the nose piece attached the fuel element to the structure, and during a disassembly or overhaul, a rod was pushed up through the middle, which activated this latch, disconnected it, and the fuel elements could be removed towards the rear. The total fuel content of the core was 500 pounds of uranium-235 in the form of fully enriched uranium dioxide contained in an 80 nickel 20 chrome alloy. The weight fraction of UO2 in this mixture varied from 0.42 to 0.27. The first three stages of the core had a loading of fuel 1.5 times the average. The fourth and fifth stages had a loading of 0.9 times the average. Both of these variations were to allow the core to operate more isothermally. That is, in order to maintain somewhat of a constant temperature down the entire length of the core. Provisions were also made for boron steel strips to be placed outside the fuel support tube for the purposes of fine power shimming. In the reactor assembly, the diameter of that center moderator bar incorporated in the fuel cartridge was varied at 7 different radial positions within the reactor. And again, this was done in order to get the radial power flattening. The idea in the power flattening was to have the fuel element operating at its maximum temperature evenly longitudinally and evenly radial, because then you can get the maximum power density out of it. The individual fuel elements, therefore, in each of the zones had a different number of rings, and the number of rings was varied along its longitudinal length in order to achieve this power flattening. Next one. I want to talk now about the trifluted moderator. The moderator sections of the XMA-1 core were designed as unclad zirconium hydride triflutes, having the shape pretty much shown in that section of the picture there. This picture shows a complete hydrided moderator assembly. In the core assembly, the moderator cooling air passed through a series of 4 holes in the moderator section through the cooling holes in the triflute and exhausted to the plenum area at the rear tube sheet and at the end of the triflutes. The moderator assemblies like this consisted of 6 full triflutes at the center of the reactor, or there were segments made up of 2 full triflutes, 2 partial triflutes, and 2 arch segments clustered around a single support tube. And there were 55 assemblies of this type in the reactor. We have a photo here that shows this is a full triflute here with its cooling holes in it, and this is a partial triflute that fit in various other sections, also showing its cooling holes. Side, yeah, that we're done. No, side reflector. The XMA-1 side reflector was designed to be fabricated from unclad reactor-grade beryllium. As shown in this chart, the reflector was constructed of 84 separate segments or blocks for structural stability. Each block was supported by 2 bolts, one of these bolts being a stationary bolt and the other one being what they referred to as a swing bolt. And that bolt was designed to take up to allow for the thermal expansion and contraction of the moderator shell. Like the rest of the moderator, each of the reflector assembly was internally cooled by air that passed through its longitudinal holes. This air being the same air that went through the reactor and through the engine. The reflector whole shell was a 1-piece right circular cylinder with support flanges at each end. The shell was designed to cantilever from the forward tube sheet, and this support the aft sheet and the side reflector. It also provided the air seal for the shell coolant and the core void. The shell was fabricated of aged Inconel X for operation at temperatures of 1100 degrees Fahrenheit. From our experience with Heater 1 and Heater 2, it was found that we experienced quite a bit of thermal distortion of the control rods. The control rods were in fairly narrow clearance holes, and there was always the concern that uneven heating would cause them to bend and jam them in their own holes. In consideration of the problems of non-uniform heating and cooling in the reactor control rod and the control rod guide tube deflection and distortion, a rod design was conceived that would move freely in a distorted tube, even though it itself was distorted. In this design, the control rod was made up of individual sections. There were 5 sections, 4 inches long apiece, that made up a total poison section of 20 inches. Let's look at another chart here. The individual segments were 4 inches long. This chart here shows 4.8 because it's from it's from the X140. But what I'm trying to show here is that these sections were joined by straps diametrically opposite from each other. These straps had enough structural integrity so that you could push on them and on the whole rod without having it collapse. But at the same time, they would not bend in their long direction, but they would bend in their narrow direction. And this gave the rod the ability to maneuver itself around any thermal distortions in the reactor itself. My name is John Tenhundfeld. Today we are going to cover the design and development of the ceramic reactor at GE Aircraft Nuclear Propulsion in Cincinnati, Ohio during the 1950s. Our narrator today is Otto Woike, who was an engineer in advanced design at that time. Otto?
John? At GE A&P, a number of ceramic materials were recognized as having potential value as fuel-carrying materials due to their inherent refractory properties and good strength above 2,500 degrees Fahrenheit. Thus, feasibility studies toward a ceramic fuel element began in 1954 with the nuclear ramjet missile as an initial application under Austin Corbin. In this chart, we have shown the silicon carbide, molybdenum disilicide, beryllia or beryllium oxide, magnesia, the zirconia, and alumina. These were the primary refractories that were studied during the 53-54 time frame. By 1955, the R&D effort on fueled ceramic materials was accelerated in the A&P research labs. Focus was now on beryllia as the moderator, fuel carrier, and structure. Preliminary designs followed of a slab and tube ceramic reactor proposed by Lou Feathers. This study continued through 1958 as the D101 test reactor. It was vertically mounted and was to use the core test facility from Heater 1 and power two J-47's modified turbojets. With a compressor discharge temperature of 400 degrees, the core was capable of 1,660 degrees Fahrenheit, when the average fuel element max surface temperature was 2,400 Fahrenheit. The power level was 44 megawatt. Would you pass me the cell? A typical cell for this reactor, there are slabs of BEO in triangular form around here, and there's another triangulars all around here, and then at the interstices, there's a control rod and in a tube, an Inconel X tube, which is a support tube, which we'll show you later in a sketch. There are gussets which hold the slabs together during the assembly, and the fuel elements are loose in here. And they have to be loose because when this goes to power, the fuel gets up to temperature quickly, and the slabs with much more material here, they take longer to get the temperature. So this is one cell of a typical cell of the slab and tube reactor. And like I mentioned, the control rod is about 3/10 of an inch, just a shade larger than the one in here. Thank you, John. The cross-section of the 101 reactor, you can see the typical cells with the fuel elements in them. And the slabs, there are 90 cells, and this is a quarter section. There are 90 cells, the equivalent cells in the reactor. There are some half cells out every 60 degrees. There's a 59-inch diameter with beryllium blocks around the outside, and then there are beryllium oxide slabs in the reflector, and the core diameter is about 44.7 inches. There was almost 7,000 fuel channels in the cross-section, and the number of tubes, fuel tubes in the entire reactor was almost 63,000. The number of unfueled tubes was about 28,000. The unfueled tubes were above and below in the reflectors. An axial isometric shows this particular reactor with, in red over here is the active core with the fuel elements, and then above it are 3 rows of fuel elements and moderator slabs, and down below at the aft reflector, the single row. The diameter of the total reactor is 59 inches. The core diameter in here, where the fuel tubes were, is 44.7 inches. And the length of the reactor is 56 inches, but the length of the core was 38 inches. There were 37 control rods in the active core. There were 9 tiers of slabs and 90 cells per tier. A 3-tier mock-up, a full-scale mock-up, was built of this reactor. Again, you can see the 90 cells with the control rod locations. Now, instead of control rods, these are the tubes that the control rods would ride in. They're Inconel X tubes. Now, this slab mock-up is actually plastic, where the plastic simulates the actual weight of the BEO. There was a weight adder put into the plastic when it was cast. Again, you can see the beryllium oxide section around through here and the beryllium mocked up around the periphery. So this is the mock-up which was used for assembly purposes, and it was used for some of the testing that was done on this. A 2-tier mock-up was built with 24 cells using actual BEO slabs. Circumferential bands provided radial loads onto the BEO slabs. Gussets and pins were used for locking these together and were left in for the testing. The BEO tubes filled one of the cells. It's pretty hard to make out, but it's in this particular cell here. During vibratory tests at 1.5 Gs, relative motion occurred between the slabs and between the tubes from 20 to 200 cycles per second. Test results showed chipping of the BEO slabs and breaking of the gussets and pins. The gussets and pins were removed, and a second test run, shifts in slab positions of about 1/8 of an inch were seen, as well as more chipping of the slabs. Next, a single tier was assembled with a better structure around the outside. It's a cylinder, but it was a single tier deep. And again, you can probably see the tubes within this particular cell. Now, the gussets and pins were left out of this particular assembly. At 2.5 Gs, core rotation occurred, and some slab intersections shifted up to 1/16 of an inch, especially at the half cells. A high degree of vibration was apparent among the fuel tubes. With additional development, the D101 might have been satisfactory for use in the Heater 1 facility. However, for close coupling with the X211 engine with vibratory excitation as well as an increase in power by about 2.5 times, the D101 was designed, appeared inadequate.
When did you actually start on the ceramic reactor, Otto?
Well, I transferred to advanced engineering in 1957. My assignment was to come up with a competitive ceramic reactor design. The A&P research labs, under the capable leadership of Clay Brassfield, had made significant strides in ceramic technology. Probably the two most significant were the use of yttrium oxide to stabilize the fuel and the use of zirconium oxide coatings on the inside of the fuel element to suppress the water vapor corrosion. Both these material developments will be discussed by Clay Brassfield. Fabrication of the zirconia-clad fuel tubes was by co-extrusion. To this process, the powdered oxides of the clad were mixed with suitable plasticizers. The fuel element mix and the cladding mix were simultaneously extruded to produce a tube, either round or hex, with a circular bore coated with the clad. This next chart shows an extruded length being collected on a half shell, and the half shell is used for controlled humidity drying of the ceramic material. The tube is then cut to length. The next chart shows the tube size reduction. In the sintering process, there's a 21% approximately reduction in size in both length. This is the after sintering, and this is before sintering. Both length as well as the cross flats or diameter dimension. If tighter tolerances are required than what is achieved here after the sintering operation, an automatic grinding operation, a straddle grinder, can be used to bring the dimensions down to within 1/1000th of an inch. Now here's another view of a piece before and after sintering. Although much testing remained to prove the fuel tube, the labs, that is, lead people like Ed Aiken, Al Clavell, Pick Turner, and Fred White, were on the threshold of a 2,500 degree beryllia fuel element that would provide 1,800 degree Fahrenheit mixed air to the X211 engine. A dependable reactor design was now needed. Now here's Clay Brassfield looking over one of their products with Fred White and John Collins. Now in this new design, my initial hope was for a hex fuel element with about 19 cooling channels and 1.5 inches across flats. I would even settle for 1 inch across flats and 7 holes. However, projected rejects during the extrusions, during the fabrication, made these what-ifs positively prohibitive, too costly.
Otto, from the changes in the aircraft mission in the late 1950s, it soon became apparent that a 1,800 degree Fahrenheit turbine inlet temperature was needed. The X211 engine itself was capable of meeting this requirement. However, the development of the metallic reactor was falling far short of this requirement. Is this where the XMA-1C came in?
Yes, John. That's the original work that we were aiming for, was for the 1C, for the twin engine, for two engines on the R-1 reactor. After several false starts, the design and development efforts led to the two-bundle reactor. The initial application was the XMA-1C to power the twin X211s. Because of a steep rise in project activity at the time, I was limited to one designer, but I was assigned the best, Warren Berard. He personally provided all the initial drawings. His zeal and optimism were contagious. The other key member of the design team was Warren Pollington, a contract engineer. He provided the complex analyses. Both were sound idea men. The initial design, and especially the three-tier development work, was based on the XMA-1C. However, to simplify this narration, I'll concentrate instead on the follow-on design, the D141. It was designed as a static ground test of a ceramic reactor sized to be compatible with a single set of X211 machinery and to be operated at the Idaho test station. In order to minimize costs, the reactor was to be operated in the Heater 3 facility. First, I'll describe the D141 reactor, then cover significant analyses, and follow with the development testing. On the chart, we have the reactor shield assembly of the D141, and this is sitting, if you remember, on it's horizontal, and it's sitting on like a second floor of the facility, and down below it is the X211 turbojet, where today, at that time, the J47s were on the ground floor. The
The air coming from the compressor then goes through to the front end of the reactor, through the reactor, out past the plug over here, and goes out back down again to the turbines. This is the shield plug in the front end. It's lead and water. And the aft shield plug, likewise lead and water, and the side shields lead and water. Again, these were not the purpose of the design. The design was to get the reactor going. The next chart shows a cross-section of this two-bundle reactor. It was built up of thousands of these quarter-inch tubes. There were about 141,000 tubes in the active core region. And these are some of the tubes that were used. Spaces were provided for 37 control rods within the active core. And there were 55 longitudinal support tubes throughout the reflector and the core. And the control rod ran within the guide tube or the support tube. The Inconel X guide tubes then were located, there was insulation around the guide tube, and then they were located inside of a ceramic BEO arch, or it was really just a large hex tube. It was about 1 3/8 in ID. The support tubes were externally insulated and internally air-cooled. The outer reflector was 4.5 inches thick. It was built of hex bars. There were about 90% of the tubes in the reflector were solid, and about 10% actually had cooling air going through them to cool the entire reflector. I guess I could walk around here a little bit. 41-inch active core diameter, 50.5-inch diameter around the reflector bars, and around the periphery there are pads. There are, at that time, Inconel X, later stainless pads, which distributed the load from springs, which were leaf springs around the periphery over here. And the leaf springs reacted against the shell, which is about 53 inches in diameter. There were spring adjusters at the outside in order to adjust the spring load during assembly. Also, you can go through the adjuster to pick up the inside part of the spring and pull it out for core assembly. The next chart shows one of the hexagonal beryllium oxide tubes, or bar, what we call the radial arch. And this was a short in distance and about 1 3/8 in ID. The next chart shows one of the control rods. Now, John, I believe you worked on some of these control rods.
Yes, I did, but more on the control rod actuators rather than the control rods themselves.
But this is what you call the articulated control rod, where there were sections like every 4 inches, and then there was a break. So it was completely encapsulated. It was europium oxide for the poison material, poison to the neutrons, that is. And then there were straps, strap across here and here, which would not bend in this direction, but would bend in the other direction. And likewise over here then at 90 degrees, the straps, which you can't really see, they sit right over this way. So every other one of these, they have the straps 90 degrees apart. So it does become a flexible control rod to follow the guide tube. Some of the data of the D141, the pressure shell diameter is 53 inches, the reactor reflector was 50.5 inches, the length of the reactor was 39.6. The core diameter is 41 inches, the core length 31 inches, that's the fuel area. Then the forward reflector was 5.5 inches of beryllium, and the rear was 1.5 inches of BEO, and the side was also beryllia of 4.5 inches. And like I mentioned before, it's europium oxide for the matrix material in the rod, and clad on the outside for oxidation resistance, and then 37 of these in the core. The next chart, sort of busy, but it does show the overall reactor with springs around the outside, a shell is supported by keyways, just like in the Heater 3, to the shield structure, the shield and also pressure vessel. And it's also supported at the aft end by keys. The springs are about they're 2 inches wide almost, and then they react against the shell and they react against the pads that I mentioned earlier. And this area again, the red shows the active core region. This is filled with beryllium tubes. And you can see the area where the control rod would come in from here into here. And there were forward were beryllium blocks, and aft there was a grid plate, essentially. It's a tube sheet, small tube sheet, and hexagonal in shape. And the forward shield, see it over here, so this is the plenum chamber, and then the aft plenum chamber over here. The leaf springs, I think you can probably show me against my shirt here. The leaf springs, these were actually for the mock-up, which were slightly different from the 141, but not much. And later I'll show you some of the spring rates and things, but it's rather stiff. It was picked because of the dampening effects of the leaves, for one thing. However, as far as the space allowed and what kind of spring design would give the least, require the least space within that circular annulus, and this is really one of the most efficient springs. Now, how in the world do you assemble these loose tubes when you want to build up, and knowing that there are different regions of this reactor where there are different hydraulic diameters, different IDs, and also different fuel loadings in some of these? Well, if you visualize a cartridge or a small section of that reactor, it wouldn't necessarily have to be hexagonal in size because this gets heavy. However, it's a good way to look at it. This is an area where there's a support tube coming through, the tube sheet at the aft end, the beryllium block on the front end, and these tubes are staggered. There's a half tube, essentially, and then a whole tube, and then they're all whole tubes, so you get the other end, and there's a half tube at that end. So it's just like concrete block when you're laying block and you're at your garage or somewhere. But it's done for shear strength, just like it is for concrete block walls or brick walls. Now, as far as locating the particular fuel element in the right spot, a color coding, first of all, as a system was used to, it's like electrical resistors. It's used to identify the particular fuel element. And I believe there were 15 different variations of the fuel element. So with the color coding system, and then you apply glue at the end of each end, just a little tab, no more than 1/10 of an inch wide, at those ends to hold the ceramics together until the final assembly of the reactor. So you have it in a jig or a fixture, and then you simply lay these tubes. All the tubes within one length are the same kind of tubes, except on the ends where some are shorter. So there is a very easy way of putting them together. And it's actually, the glue only serves a purpose until the final assembly. Boron steel wires are put into these tubes, into the cartridge that I showed earlier, and they poison out the reactivity at final assembly. At 600 degrees Fahrenheit, the cement, which was an isobutyl methacrylate, it vaporizes and the cartridges lose their identity. So then you have the complete bundle, and this includes through the reflector. The aerothermal and nuclear analyses of the ceramic reactors went smoothly under the capable leadership of Mel Lapides and Frank Dawson. Their parametric sizing graphs in particular were useful during the advanced design. Got some selected data here. On the 141 reactor data, the total power to the air was 107 megawatt thermal. The core pressure ratio is 0.846. Average fuel element max surface temperature is 2,300 degrees. I'll show you later a curve of that. The Mach number of the fuel exit was about 0.253. The airflow was 350 pounds per second. The pressure, 156 psia, and with the exit, 132 psi, the exit of the core of the channels. The air temperature at the inlet was 700 degrees Fahrenheit from the compressor, and the exit air to the turbines, which is a mixed air, in other words, the cooling airs that bypass and go through the core, and the 1870 degree air coming out of the fuel channels are mixed to an 1800 degree at the turbine inlet. I want to next get into what the sizes and some of the loadings and things like that. The flats is 0.256 inches. The ID was 0.18 inches, just a shade under 3/16. There were 12 variations of the ID, and there were 15 different regions within the core going radially. The ID varied from minus 8 thousandths less on the diameter to 18 thousandths higher on the diameter, in other words, a thinner wall. The clad thickness, the zirconia clad thickness was 3 thousandths of an inch, or 3 mils, and the length of the tube was 4.428 inches. The max loading, the UO2 is 6 weight percent. Later, you'll notice when you get into the 140 reactor that by that time, Clay had developed enough enough work on the fuel element to know that he could get to 10 weight percent and still have a good, strong fuel element. At this time, we were limited to the 6%. The number of fuel passages was 20,200 essentially, and the nuclear life was 55,000 megawatt hours, equivalent to 1,000 hours at Mach 9/10, 30,000 feet. So that was our design goal. The next chart shows this is on the axis, the length of the reactor from the 0 point to the 1 is really the front of the core of the fuel to the aft end of the fuel. And showing coming in the air temperature at 700 degrees and going on up to 1870 from the fuel. Remember, I said it's mixed 1800 degrees at the turbine. And then this is the surface temperature of the average fuel element. And this average fuel element reaches between 2,000, 2,400, 2,300 degrees Fahrenheit. And then slows down, it comes down to about a little under 2,200 degrees as it leaves the fuel. The next chart because of the importance of the fuel tube stresses, I'll next discuss the allowable tube bundle deflection, the minimum radial pressure required on the bundle for stability, and the max pressure, as well as the 3 methods of radial support that we finally evolved for this tube bundle. The control rods, since the tube bundle is sitting on springs, it will be essentially bouncing for G loads. If you get G loads of, we were designing for a maximum of 4 Gs down, say, and 1 G to the side. There will be occasional bouncing. As you can imagine, it's flying in an airplane, you'll be bouncing. So would the core. Now there's got to be a limit on the amount of bouncing of, say, the center line, because you got control rods feeding from the stationary, if you will, forward plug to the bundle of tubes.
I set an 1/8 of an inch as being the maximum deflection that we could stand. And we designed the control rod guide tubes and the shield plug and so forth for that. The allowable displacement of the tube bundle within that shell was established by control rod alignment. It was set at 1/8 of an inch. By dividing this bundle weight by this displacement, a system spring rate is found, which remains invariant in the design. If chosen too small, it can cause large increases in bundle pressure and fuel element unit stresses. But there's a minimum radial pressure which occurs when the radial spring gap is the largest and the spring force is the least. It occurs at the highest temperature that the support system and the tube bundle have in common. In other words, when the temperature of the support shell, the Inconel X shell on the outside, your main structure, and the tube bundle itself are at the same temperature, the ceramics will expand much less than the metal, and so the gap will increase. So that is the critical point where we have to maintain enough spring pressure to keep the bundle acting as a unit. The maximum radial pressure is the algebraic sum of the minimum pressure, that is the allowance for the inertia, plus the assembly tolerances, plus the differential expansions of the shell and the tube bundle, plus the autoclaving from static pressure in the spring cavity, plus the fuel tube creep and spring load relaxation. The latter two are functions of time, temperature, stress, and NVT, or flux or fluence. All of these variables which affected the spring gap were investigated and were controllable. As the tube bundle deflects due to the G-loads, friction between the springs and the pressure pads would most likely prevent the bundle from recentering itself, returning back to where it was in the center. So another design approach was to support the tube bundle at its periphery by a shear distribution to that structural shell. If keys were used, like we key tube sheets and things, lateral bearing pressures on them would lead to galling and seizing. However, the elliptical spring could act as a flexible key.
Now, Otto, yes. Could you discuss the spring rates and the hardware, the materials, and the spans and things like that?
First, I'll mention if keys were used like this from the pads to the shell, there would be galling and seizing, and certainly we just wouldn't work. Again, corrugated shell might be used, and again with keys around through here, we looked at both garter springs as well as a shell, which was corrugated, and it was much heavier and did not help us at all. What we did do is take the spring and use the spring itself as a flexible key between the pad and the shell. And so, John, if you'll notice, we have here a key that's built right into the spring. It's right welded right on, and it's on one end only, and on the bottom over here. It's not on the other end, so when this gets locked to the shell and this gets locked to the pad, and again the shell is this way, the other end is free to expand like this. So we really have two different spring rates. We have one which is keeping the bundle together as a unit, and the other which is keeping the bundle at the periphery, at the outer diameters, from slipping, from moving.
Yep.
On this chart, you can see the spring rate here is like, this is for the 3-tier mock-up which we built. Spring rate is like 100 psi, and it's a function of the distance, really, on the gap, the spring gap. And this is the tangential, or the pressure this way. And you can see we're up 900 to over 1,200 psi, pounds per inch on the spring. In pure shear suspension with the bundle displaced bodily, tangential loads are developed at the horizontal diameter. Internal shear strength is required to hold the shape of the bundle. Now, a lower radial spring rate can be used. when this is supported here by these keys, if you will, or that spring with the keys on it, it's like opening up, trying to open up the core into an opening here and trying to break it apart, where the maximum pressure is on the top of the tube bundle. Now in the hydrostatic system before, the highest pressure was here at the bottom, where we allowed this point to almost reach zero. So we've relocated the maximum stress point from, instead of being down here, we've put it over here. Now the obvious next step was to design for both the hydrostatic and the shear support of the tube bundle in an integrated or combined support. Again, you can show here the tangential support here to keep that deflection down, and again the radial support or hydrostatic support over here. So we now have combined, if you look over here, for the tangential, this is the support we get around the tube bundle to keep it from deflecting too far, and likewise over here, and from getting too much load is really what we're after. And then for the hydrostatic, here and here. So that is the integrated support. Using that hydrostatic rated support, the internal pressure to the G loads is highest on the lower tubes, like I mentioned. For the shear support, the internal pressure acts tangentially and are maximum on the upper tubes. For that integrated system, a reduction in both the minimum and the maximum pressure occurs. The integrated system, or the balance support, was a design goal.
What about the axial and longitudinal support of the tube bundles?
Well, the axial support of the tube bundle was a modification of Lou Feather's design for the slab and tube reactor. The retainer plates, support tubes, and forward reflector block made up this system. The primary objective was to resist the axial deformations of the tube bundle through all operating conditions. At reactor startup, the axial pressure forces are resisted by frictional forces from the radial support system. In other words, you've got a pressure on the forward end, which is higher than the pressure at the aft end, and so the tube bundle wants to slip aft. Also, there is a 1G pushing in that direction, which is small. So we're talking roughly 28, 30 psi, 28 here, and then maybe another 3 psi, which is an equivalent for the 1G. And you've got, around the periphery over here, you've got the friction, which is trying to prevent that bundle from slipping aft. That total aft pressure force is proportional to the radius squared, while frictional resistance to the tube bundle movement is proportional to the first power of the radius. Thus, the tube bundle will slip aftward, not down through here, but at that radius, at the outer radius, until the retainer plates and the support tubes take up the load. A redundant axial structure exists because you got 55 tubes, and they're not all the same length, they're not all exactly the same temperature, same tolerances and stuff like that. So the 55 support tubes pick up loads at different times, depending on tolerances, temperature differences, and so forth. A load relief device, a spring on the forward end over here, was placed at the forward end to prevent axial distortion of the tube bundle and to assure almost equal loads on all these retainer plates. The total preload on the tube bundle must exceed the side restraint imposed by the peripheral friction that I mentioned at the pad. And it's important that the tube bundle returns to its original position at reactor shutdown.
Otto, there was some concern about unequal load sharing in the load on the tubes, or pressure magnification. Could you amplify a little bit on that?
Okay, I'll try. That's one area that was really a puzzler at first. The question of bridging and going around a number of tubes. Well, what about the tubes that are doing the bridging? What kind of loads are they experiencing? This pressure magnification within the tube bundle was a major concern. The ceramic elements within the tube bundle vary within the manufacturing tolerances and so forth. This permits some elements to accept more load than others in the form of local pressure concentrations. Both analytical and experimental means were used in attempts to assess the magnitude of these pressure concentrations. Now this is within the tube bundle itself. One analytical approach assumed that undersized tubes may be assembled adjacent to each other to produce cavities within the tube bundle. Pressure concentrations are expected to occur around the cavity due to the bridging of the load. By applying the analogy of a disk with a hole in it, this would be then the load depending on the size of the hole. This would be the loads that would apply to these tubes around that hole. The stress at the edge of the hole can be determined as a function of the hole's size relative to the size of the disk. When a large cavity is introduced with a radius up to a half of that of the tube bundle radius, which is rather large, the tube bundle pressure might approach 3 times the radial pressure. The inward radial pressure, of course, is 0. In another analytical approach, an adjacent pair of undersized tubes might introduce a pressure concentration factor of 3 times that average pressure. The largest load multiplier found during analysis for that D141 was a factor of 3. Several experimental tests were run, but were largely unsuccessful. Strain gauges attached to various small and large tube bundle mock-ups failed to measure dimensional changes as the radial pressure, shock, and vibratory forces were varied. Another test introduced successively larger cavities into the pressurized tube bundle and was considered a count the cracked tubes approach. The stability of the tube bundle in redistributing the loads and bridging around the cavities was impressively demonstrated, but the tubes did not fail. The tests gave confidence that excessively large concentration factors did not exist. A value of 3 was therefore chosen for the design.
Otto, what about the stresses in the fuel tubes themselves?
Thermal stresses are a function of the overall geometry of the fuel element, and the exact analysis is rigorous. However, it was found that the D141 elements could be treated as an equivalent round tube with the same materials cross-section. The max calculated thermal stress using elastic theory turned out to be about 9,700 psi, and it occurred in the region of the tubes with the minimum hydraulic diameter, that is, the greatest wall thickness. The mechanical stresses in the fuel elements resulted from radial and axial loads imposed on the reactor. The radial loads were of primary concern. Beam bending with loading at the center was the most significant mechanical stress. It resulted from the radial pressure between 2 or more elements with appreciable camber being squeezed together and restrained. Ring bending, in other words, squeezing the tube this way, depended on the type of loading, whether 2 or 3 or 4, 6 sides were loaded. But the photoelastic analysis showed the worst stress when opposite sides of the fuel element were loaded. Plaudits are deserved by Jim McConnelly and Art Ross for reducing the complex stress analysis of the fuel tubes to practical use in this coming section. The total stresses at any point in the fuel element were obtained by combining the individual stress contributors algebraically and using the principle of superposition. The time of occurrence, the location, and the direction was considered in the combination. In other words, you have to add tensils to tensils and whatever. Maximum tensile stress for ceramics was of more concern than were the compressives. Total combined stresses were found. First, the initial elastic tensile stresses occurring during operation, and then the residual tensile stresses at room temperature. You have that tube there? The residual stress, if you would imagine, when we first put the bundle together and at cold, we just have a straight fuel tube, say, and then as it heats up, the core expands, and you can imagine now you've got different kinds of thermal stresses as well as mechanical stress, but I'm just going to show a mechanical stress. At temperature, the tube might be like this, where there was no stress in either the outer or the lower fiber.
when I bend it like this, you've got a tensile stress on the upper and a compressive stress on the lower fiber. Now, at temperature, if there's enough creep, what would happen then, if you come back down to room temperature, the spring will press down and actually force the thing to reverse so that the lower now would become tensile and the upper one would be in compression. So both of those had to be looked at. The combination of residual temperature stresses assumes that complete relaxation had occurred and consequently gives the max value. The design criteria for the D141 fuel elements required that the ultimate stress be compared to the strength available, that is, the average modulus of rupture minus 3 sigma, or the standard deviations. The validity of the fuel tube and of these calculations was demonstrated by extensive development testing, which will be discussed in the ceramic materials section later by Clay Brassfield. The ceramic reactor development tests, there was significant development testing in support of the 141 design program, and is mentioned to illustrate the degree of confidence with which the GEA&P department recommended the ceramic reactor in 1959. Nuclear tests of a preliminary critical experiment were performed by Jack Simpson's engineers to obtain experimental data on shield worth, control rod worth of structural materials, power distributions, and fuel loading. The tests included 3 successive assemblies. The nuclear analysis was led by Frank Dawson and included Gene White and others. Typical of the aerothermal development testing in support of the 141 were the airflow tests required to experimentally determine air channel friction factors. These tests, needed by Mel Lapides and Bob Spira in design, covered the range of Reynolds numbers from 7,000 to 35,000 and were made on a series of 12 stages of tubes. The 3-tier structural tests will be next. The 3-tier ceramic development mock-up was 56 inches in diameter for the bundle and 14.5 inches long, half of the core length. And again, that was the dimensions for the XMA-1C. This tube bundle weighed as much as my Saturn station wagon. The structural tests explored first the assembly procedures and the tolerance stack-ups with 0.372-inch tubes, containment of the bundle within 1/8 of an inch, pressure load distribution within the bundle, especially load multipliers acting on the fuel tubes, behavior of the assembly in separate tests of shock loads, vibrations, sustained G loads, axial, aero, and friction loads, and temperature cycling to 900 degrees Fahrenheit. This is a shock test setup. It's probably difficult to see. However, this is the shell and shows the adjusters on the outside to get the proper spring pressures and change the pressure depending on the requirement. And the shock comes from here, and there's reinforcement even on the shell to make sure the shell can be understood as far as the G loads on it. It's a high G system. The leaf springs covered 10-degree arc. So the leaf spring covers a 10-degree arc here. The pads were 5 degrees, and the pads on the inside towards the bundle locked in with the tubes so that there was always a connection, a shear connection with the tubes. Rather than putting just half tubes or something like that on the outside, we wanted to actually get a lock between the pressure pads and the hex bars on the outside. The reflector hex bars measured statistically 0.365 inches on the flats, while the core tubes were 0.372. Another slight radial cracks uniformly around the bundle appeared. They were conservatively set approximately twice the expected differential expansion. And again, the differential expansion was the cool core and a hot reflector at shutdown.
Longitudinally, there were, in the buildup of the three-tier mock-up, there were 3 tubes axially. However, then, in order to get that shear connection, we put in a smaller tube on each end for every third, I believe it was, tube. Although we actually assembled 19 tubes at a time. The tubes were assembled into cartridges, like I showed you before, and using an adhesive, which was that same isobutyl methacrylate, and was removed by heating to 600 degrees Fahrenheit, and the tubes were free. The ceramic tubes that were used were Alsamag number 196 because of its low cost and low toxicity factor. Its density and low temperature mechanical properties were similar to BEO. Accordingly, room temperature stresses in the mock-up corresponding closely to room temperature stresses in the reactor tubes, and that was pretty important.
Otto, did the 2 bundles of the 3-tier test mock-up stay within the 1/8 inch design allowance for the control rod tubes?
Well, a good time for a question like that. The shock tests we'll mention next. Measurements were made of the 3-tier mock-up acceleration and radial displacement. In some cases, a load cell replaced a radial arch to measure the radial pressure on a tube within the bundle. The load cell data showed a load multiplier acting on the tubes of approximately double the average radial pressure at the core periphery. The first series of shock tests used a hydrostatic support. We did not use the keys on the springs. Loads up to 4 Gs cause a peak deflection 82 mils, or a 0.082 inch. Residual deflection or hanging up from friction forces were within 20 thousandths, but appeared to be increasing. In other words, it was not completely back to center. It was within 20 thousandths, but it looked like it could go beyond. And when you're dealing with friction, you could certainly see where that would continue like that, although it would bounce around. The core was disassembled and modified to include the shear ties of the springs. After a series of about 25 shock tests, again up to 4 Gs, the peak deflection remained below 70 thousandths, while residual hang-up or recentering of the bundle relative to the shell remained below 10 thousandths of an inch. Now that's pretty darn good when you're thinking of a 5-foot bundle weighing as much as my car.
Yeah.
These shock tests verified the deflection of the bundle varies linearly with the acceleration, or the G loads. The shear ties contribute to retention and centering of the bundle. The undersized reflector bars resulted in gaps in the region. These gaps permitted some movement within the bundle. However, high-speed movies failed to produce any detailed knowledge because of the very small motion involved. It should be noted I had set the reflector bar undersizing at twice the value expected. This was done to exaggerate the effects of the radial gaps during tests to better understand whatever the effects were going to be. The axial loads were applied via pressure through a neoprene diaphragm. The simulated air drag load was carried from the aft retainer plates, axial support tube, and to the forward preloaded springs. 5 series of tests showed that the tube bundle acted as a unit assembly as predicted. A series of hot gas flow tests were run using the 3-tier mock-up. The forward end of selected air channels were plugged to increase the overall pressure drop across the core. Excuse me. The delta Ps of 20 psig and temperature of 900 degrees Fahrenheit were simultaneously applied to the reactor. Airflow was cycled incrementally under steady state temperature. Radial displacements and loads in 12 of the axial support tubes were measured. The results were the core did not settle. It remained centered. The springs worked. The axial support system limited the peak load in any tube. It would also absorb the differential thermal growth between metal and ceramic parts. The bundle returned axially to its cold position. Exploratory vibratory tests were conducted on the 3-tier mock-up. at GEMSD, the Missile Space Division in Philadelphia. The mock-up was excited at various frequencies and amplitudes to a maximum of 3G. Sweeps were made over the full range from 20 to 120 cycles per second. The engine ran at 5,000 RPM. The sweeps were then followed with 3 one-hour steady-state endurance runs. Tests were performed for 2 radial loads, 17.5 and 10 psi. The results? No deterioration or gross dimensional changes were detected. A final vibe test consisted of removing tubes to form 2 cavities through all 3 tiers. The result? The structure remained sound and showed no evidence of progressive disruption. We did the component test on the aft reflector, aft retainer plates, the support tube insulation, springs, the coefficient of friction among various materials. The materials we're interested here, as well as the final reactor, including the alcemag tubes. And sure have to thank Ernie Ratterman and Spud Eckert and all these other test engineers. You probably mentioned a bunch of others, John Blake, others. They did a commendable and thorough job.
Well then, how did the single engine shaft through the center of the core design come about?
In the summer of 1959, Garth Leith asked me if a pipe could be placed in the center of the tube bundle to allow space for the X211 midshaft. Garth had already determined that the center island was feasible from a nuclear and thermal standpoint. I said a thin liner should be ample since it's constrained by the tube bundle. In other words, I demonstrated with a round wastebasket. You can squeeze it this way, but if it's kept from moving this way, it'll do the trick unless there's a third kind of cycle that comes in for buckling. The chart here shows a buckling test of the duodecagon on a periphery liner. And you can notice it's quite thin. And it failed at 285 psi, which certainly is quite a bit above what we were talking about, what we were expecting. The next chart shows the initial advanced design of the XNJ 140 core, with the liner here and then the shaft through here. And these now are just tie rods. They're not control rods in the active core region. The control rods are out in the reflector region. And again, we got the shell and the springs and the pads. These springs covered, rather than 10 degrees like we had in the mock-up, for example, the springs in this case covered 15 degrees around the periphery. Because we were sure of the integrated system, we could have a lower spring rate. So obviously, the farther apart you make these, the longer you make the spring, the smaller spring rate you have. Various tests of a liner in the 3-tier mock-up were successful. Here is again a duodecagon, the liner, and it went through all the usual tests of shock tests and everything that we mentioned before. And it was very successful. There wasn't anything unusual at all about it. Better get a drink of water. The final chart shows a 3-tier with a liner and with a 10-inch cavity after completion of a 5G shock load. So here's the liner. You see some of the instrumentation on it. And these tubes were pulled out before the shock tests with the idea of they seemed to be tight, and so he pulled out all and pushed out all the loose tubes they could during vibration. They pulled them out, and so we knew that this here was bridging around here. The cavity was introduced before the test and remained unchanged. It amply demonstrated the self-healing and bridging in the ceramic tube bundle design. In the fall of 1959, the ceramic reactor design and development was transferred to final design. The new owners scrutinized the design and testing and found it sound in all major areas.
Otto, I think to close out, it would be nice to acknowledge some of the engineers who worked on the final design.
I put a few of them down on the next chart. I just hope that I haven't forgotten too many of them.
Well, it's always a problem.
But the players alphabetically are Ken Anstead, who worked on the radial support system,
Ray Cook, Roy Eckert, Ernie Elevik, Pete Flagella, Dave Flittner, Jim Hagan, Bill Hunter, Buck Jordan, Jim Kepler, Dick Lorkey, Dick Molman, Cal Moon, Charlie Schiltz, Aubrey Smith, Len Wessendorf, Dick Wilkie, Jack Cole, there are others.
Okay.
Well, with that, I guess we can conclude.
I think that.
Proceed with the description of the reactor. Isometric view here, which shows some of the main features. It shows the engine shaft passing through the axis of the reactor. It shows the active core, which is about 30 inches long. It shows the control rod guide tube. I believe this is the control rod, penetrating the inner part of the reflector. And there are 48 of those control rods around the periphery. There's a front reflector, which is 4.75 inches thick, and there's a rear reflector, which is 1.5 inches thick. Okay. We'll get pretty smooth about this one. In this view, you see the fuel elements in the active core, which is a radial segment. I'm sorry, an annulus. The control rod guide tubes and the control rods are shown on this circle. There are 48 of them. This is the outer reflector, which is mostly solid beryllium oxide with appropriately spaced cooling holes, cooling channels. And this reflector grades the temperature from about 2200 F in the active core down to about 1100 F at the outside. So this retaining springs out here can run at 900 F. At the inner radius, there's an aluminum oxide reflector, which is about 1.25 inches, 1.5 inches thick. There's at the axis, there's an aluminum oxide reflector, which is about 1.5 inches thick, and which grades the temperature from 2200 F in the core to about 1400 F at this Inconel shaft liner. Now the active core is made up of fuel elements which are beryllium oxide. The active core is made up of fuel elements which are beryllium oxide impregnated with fully enriched uranium dioxide and stabilizer materials. Beryllium is a good moderator and is frequently used as a reflector for reactors. The beryllium oxide is a stable high-temperature ceramic, and so this fuel tube is used as the fuel carrier, the moderator, and the structure for the active core. This is an unloaded fuel tube. If it were loaded with UO2, it would be black, but basically it's a small hex tube about 1/4 inch across flats with about a 0.167 inch hole, and it's about 4.38 inches long. There are a total of 25,000 channels in the core. The fuel element
is internally clad with a 3 mil coating of zirconium oxide.
This coating is present to counteract a hydrolysis reaction between BEO and the moisture in the air. And this reaction product is a white crystalline growth that tends to grow into the airstream. The cladding doesn't suppress fission product release. The fission products that recoil from the fuel near the surface enter the airstream directly, but there is no evidence that fission products or fuel diffuse from the interior of the tube. So let's go to the next table. This table shows you some of the gross characteristics of this power plant. The number which should calibrate everybody is that the reactor power is about 50 megawatts, and this number applies at 30,000 feet with the airplane flying at Mach 9/10. The reactor inlet temperature at that point is 582 degrees F, and the turbine inlet temperature is 1740 degrees F. The reactor pressure ratio appears on this chart. It's 0.857, and the pressure ratio is a very important variable, and one in which quite a few trade-offs are involved. The nuclear designer would like to have the core solid, so it takes less fuel, has less of an inventory. But the airflow thermal designer wants to have the core with lots of porosity so that the pressure drop is small. In this case, the trade-off was made at this point, and the frontal area is 47% air and 53% fuel. The nuclear characteristics of the reactor are expressed kind of by the fuel inventory and the excess reactivity requirements. So let's go to the next chart. The fuel inventory for this machine is 87 kilograms of uranium oxide, fully enriched. The excess reactivity at that loading is about 5.9%. 1.5% is needed for equilibrium xenon at 50 megawatts. And burn up and fission product poisons over the life of the core account for about 2.9%. The temperature effects are relatively small. In fact, listed as 0 in this chart. There's a margin of 1.5% for error, and the control rod worth is 10%, which gives us a fairly comfortable margin for scram. The next figure I'm going to show you is the longitudinal power distribution in the reactor. Power distribution is all important in a high-performance machine of this type, and it needs a lot of discussion. I'll switch. Curve shows the longitudinal variation of the volumetric power generation, watts per cubic centimeter or whatever units you want to use, on a relative basis, with 1 being the average. And this solid curve, pardon me, but in this figure, the control rods are inserted about 18 inches, a little more than halfway. And that would correspond to the clean startup condition of the reactor. Now, near the inner radius, the curve is quite smooth, and it's typical of the classical distribution you get with a fairly thick front reflector and a fairly thin rear reflector. As you go out on the radius next to the control rods, the power is peaked further aft. But this is of not too much consequence. It's sort of a second order effect, as I'll show you in the next slide. Don't change it. This is a calculation of the longitudinal air temperature distribution for an average tube. And this peak here is about 2200 degrees, and the exit is about 2010. The peak occurs near the aft end of the reactor, but because the air has to be heated all along here, and it reaches its maximum temperature at the end. So whether the power peaks at this position or this position is kind of a second order effect on this temperature distribution. Over here I have a schematic plot that I drew that shows what the neutron flux distribution would look in the radial, what it would look like in the radial direction for a reactor of this type. There is a fairly substantial peak near the reflector, and this is because the fast neutrons generated in fission stream out into the reflector. They get slowed down, and about half of them come back towards the active core, but the fuel has such a high fission cross-section for thermal neutrons that the neutron flux is quickly attenuated. That's the physical picture. The difficulty is that if the fuel elements were sized to handle this maximum power, they would be loafing in the center of the core, and therefore the performance wouldn't be very good at all. Well, the homogeneous nature of this reactor gives us two ways to try to equalize the temperature distribution across the radius. One of these is to vary the hole size. So as you put small holes in the low power region and big holes in the high power region. The other way is to vary the fuel concentration. And variation of fuel concentration was the mechanism that was actually selected for this power plant, and I believe this chart will show, okay, this shows the fuel concentration in the active core versus the radius. What this means is that the entire length of the core is run at the whatever concentration you see here. Maximum is about 10% where the dip in the neutron flux would occur, and the minimum is about 4.5% out near the reflector where this large peak was shown. The radial power distribution now looks like this. And this is plotted for 3 different control rod positions. This curve over here at the top is for control rods inserted 18 inches. The power is highest near the center of the reactor and falls off near the outside. The lower curve here is for control rods fully withdrawn at the end of life, and it is low in the center reactor and peaks near the reflector, as we saw before. These curves are hash mark shaped because there's constant fuel concentration in each of these regions with a varying neutron flux distribution. Okay, now having adjusted the power distribution by means of variable fuel loadings, we now can ask what effect this has on the fuel element temperature distribution. Switch. Chart shows the radial variation of temperature with the variation of temperature with radius. It looks a lot like the power curve, but this is now the maximum surface temperature along the length wherever it occurs. And you can see again that for early in the life of the reactor, these peaks here are about 2,300 degrees, and it's very crowded over here, but the solid lines are falling off near the reflector because, as the power did, near the end of life, the center of the core is running at about 2,000 degrees, and it peaks near the outer reflector at that point at again about 2,300 degrees. So there's from the average temperature, which is 2200, to the maximum temperature, there's about 120 degrees imposed by the small variations in power within each fuel region. It needs to be emphasized that these power distributions were all obtained from a critical experiment. And the critical experiment was partly loaded with actual fuel tubes. It mocked up the variable fuel distribution. So these are not horseback calculations. These are good measurements. Airflow tests have been run to establish friction factors and heat transfer coefficients. And therefore, the predictions of fuel element temperature that we've just discussed have a pretty high confidence level. Now, there are other fuel element temperature perturbations that have to be considered. At the top, we have 120 degrees. That's due to the uneven power, as we showed you in the previous chart. We now talk about fuel element size tolerances. 1 mil on the hydraulic diameter is worth about 20 degrees. 1 mil on the flats dimensions, about 15 degrees. A 3.7% allowable variation in fuel loading is worth about 40 degrees. All of these effects from tolerances add to 100. There are other things that have been taken into account in terms of the possible uncertainties left remaining in the measurements that were made in the critical experiment and in our knowledge of the heat transfer coefficients and airflow characteristics and in the lineup end to end of the tubes in the channel. And these numbers add to about 124 degrees. And then for the internal temperature rise from surface to corner in the fuel element, we have about 30 degrees. These temperature perturbations are to be added to the average fuel element temperature, which is 2200 F. And the 120 degrees built in from power flattening is shown here. That gets you up to 2330. All these allowances for fabrication tolerances, measurement uncertainties, bring you up to 2530, which is the stated maximum fuel element temperature at cruise. The maximum fuel element temperature tends to be a rather controversial number, and people tend to regard it as a locked-in thing where if you exceed it, you're done, and if you don't get to it, your performance is bad, and so forth. But as we saw in the preceding charts, for one thing, the maximum temperature walks around the reactor during its life. And for another thing, the estimate that we have is based on the direct stack-up of a lot of tolerances which might be better added statistically. So that I would like to convince you that this is actually a fairly conservative design. And this chart shows the percentage of fuel elements at percentage of volume at a given temperature. You can't read it, but along the axis is temperature. This is about 1200 degrees, and this is about 2400 and 2500 degrees out here at the tip of the curve. The average temperature, 2000 degrees, is about here, and so the bulk of the reactor is running at fairly low temperatures, and only a small portion actually exceeds the average temperature. I think another mitigating factor I would like to mention is simply the fact that there has not been enough experience with this kind of fuel element to understand just what happens at the end of life. Whether the failure mechanism is sudden or whether it's gradual, and what just does happen if you exceed this maximum temperature for any extended period of time. This isn't to trivialize the fact that one hot channel may plug up and begin to cause progressive deterioration in the core. The point is that none of these things can be considered hard and fast until we have further operating experience. Now, there are some auxiliary cooling functions which are necessary, and they detract somewhat from the performance of the system. And I'd just like to take you through those real quickly. This chart shows you what the operating temperature of some of these other components is. And for reference, I've also put the inner radius, the thickness, radial thickness, and the temperature. The shaft tunnel liner, for instance, runs all together at 1400 F. Now the inner reflector, which is 1.8 inches thick, has its maximum temperature next to the core, 2200, and the minimum temperature is 1400 next to the liner. And this temperature is dropped from this level to this level by judicious placement of cooling air tubes. Obviously, there's more cooling air near the periphery than near the core. Here's the active core region. It's 13.9 inches thick, and as we said before, runs at a maximum temperature of 2530 and a minimum of about 1890. These are different kinds of numbers from these up here. The outer reflector is 8.5 inches thick. Its temperature is 2200 degrees near the core, and that is graded down to about 900 degrees so that the support springs can run at 900, which is their operating temperature. I'll just go, and can you come in a little bit more on that? Okay. All of this auxiliary cooling takes bypass air. And the way this system has been configured to date, the fuel elements only carry 80% of the air that eventually gets to the turbine. The inner reflector carries 0.9%, the outer reflector carries 4%, and by the way, the exit air temperature is 1240 at the inner reflector and 1120 at the outer reflector. The springs take up 1%, pressure pads 1.3%, the control rods and their guide tubes 1.5%, and that air exits at 1050 F, and the aft retainer assembly, which is mostly metallic, operates with air at about 1025 degrees F. And this gives you a mixed air temperature from the core of 1800 F. Now another 9% is taken away to cool the shield and some of the engine components. This is about, as I said, 9.1%. It eventually comes out at 1120 F, so that mixed turbine inlet temperature becomes 1740. Now you can come back to me. Now that table shows that the amount of bypass air required to cool the auxiliary components is significant. And on the other hand, the knowledge of heating rates in most of these components is quite a bit less accurate than the knowledge of the fission heating in the active core. The heat that gets to these components partly comes from conduction. It also comes from neutron scattering and gamma ray absorption, and these are both more difficult to calculate and to measure than the fission heat. So more accurate knowledge of some of these heating rates and airflows and perhaps an upgrade in the temperature capability of some of these components may lead to further performance improvements, even if they are somewhat small. Well, the overall results of these nuclear and thermal studies indicate that the predicted performance can be adequately achieved within 1,000 hours life of ceramic fuel. The nuclear results are especially good because they're backed up by the critical experiment. And prediction of the maximum operating temperature of the fuel is dependent on the estimation of many perturbations. On the other hand, the end-of-life mechanisms for the fuel are not totally understood. But at this stage, the achievement of the operating characteristics of this power plant looks good. It looks highly possible.
In mid-1959, a decision was made by the Department of Defense to change the objective of the aircraft nuclear propulsion program from the development of a power plant for a specific weapon system to applied research and development of a system capable of propelling an aircraft at a speed of from Mach 8 to 0.9, Mach 0.8 to 0.9 at an altitude of 35,000 feet. The reactor in this system was to use materials capable of providing a life of 1,000 operating hours at the specified performance level. Although we didn't know it at the time, this was to be the last of many changes in program direction for which the ANP program leadership was to be severely criticized in an evaluation report issued later by the General Accounting Office. In view of the revised objective, it was determined that the XMA-1A power plant could not achieve the necessary performance level. Studies were initiated to evaluate various power plant configuration and potential reactor materials. These studies culminated in March of 1960 with the decision to proceed with a system consisting of a single X211 engine with its shaft penetrating a beryllium oxide reactor. This power plant was designated the Experimental Nuclear Jet 140E, and it appeared to have the best chance of meeting the desired performance objective and still exhibiting the potential for future growth. Its development was approved, and a target date for a ground test in the flight engine test facility at the Idaho test station was set for December 1962. This test was designated the Advanced Core Test since the X211 turbo machinery had already by this time undergone extensive chemical testing. A date was set for flight testing in the Convair NX-2 prototype aircraft for 1965. Based on work with Convair, design requirements consisting with the Department of Defense guidance were established. These were conditions of airflow, temperature, pressure, thrust, and other parameters. The design points were then distributed over the required 1,000-hour reactor life. These various design points are shown on our first chart, where the ground checkout time was 20 hours, 5 hours was allocated for chemical takeoff, 20 hours for climb to station, and 885 hours for cruise on station. 20 hours was allowed for maneuvering while on station, and 50 hours allowed based on 2-engine operation or a single engine out on a 3-engine configuration. The power plant also had to be capable of operating at any speed or altitude up to Mach 1 at 45,000 feet. As a general rule, extended operation at low speed and high altitude would have extended the life beyond the 1,000 hours, while extended high-speed operation at low altitude would have decreased life expectancy. It was assumed that the reactor would be replaced during normal engine overhaul at 1,000-hour intervals. Once the basic design requirements had been determined, a number of studies to fix the material selections and design configurations were made. The selection of materials and the configuration of the reactor has been covered previously in the discussion of the 140E reactor. One point that should be made, however, is that the shaft penetrating the reactor received heat from both thermal causes from the hot active core as well as radiation heating in the material. Therefore, significant airflow was provided through the shaft for cooling. The configuration study was done in depth with a preliminary design made for each of 3 major configurations. The first of these was basically the XMA-1 configuration consisting of 2 engines but using the beryllium oxide core. The second was an integral single engine configuration where the shaft of the reactor, the shaft of the engine penetrated the reactor. The third had the reactor in front with ducting back to the engine. As far as performance, each configuration was to provide exactly the same thrust as a function of speed, and hence they were identical in performance. However, the twin-engine configuration suffered a distinct problem in that engine failure robbed the system of the thrust from 2 engines. Both of the single-engine systems suffered some slight or some weight disadvantage because of the fact that it requires less shielding for one reactor providing the same power as 2. However, it was offset to some extent by placing the engine side by side, and in the integral single engine configuration, the turbo machinery itself, particularly the compressor, provided significant additional shielding. Further, the integral single engine unit had the advantage that the elimination of any internal ducting significantly reduced the weight. Ultimately, it worked out that 2 single-engine systems weighed approximately the same as the 2-engine configuration. The maintainability of the single-engine inline system was enhanced since the system was compact and comparatively easy to handle. Externally mounted components and disconnects were unobstructed by ducting, and vertical assembly and disassembly was readily achievable. Consequently, the integral single configuration was judged to be the most suitable from the maintainability standpoint. The result of the advanced configuration study was a recommendation and subsequent approval of the single-engine integral configuration for development to meet the Department of Defense objectives. The configuration is basically as shown here and on the model. Originally, the thing was designed to have some integral interburners for chemical operation. Later, studies were made to remove the interburners with the result that the shielding weight could be reduced and the shaft length could be reduced. The chemical system would then depend on afterburners. This configuration of the engine was identified as the XNJ140E-1 for the advanced core test version, and as the XNJ140E for the flight version. These are the major characteristics of each of the two power plants. The objective version, the XNJ140E, was reduced by about 4,000 pounds in weight, and the turbine inlet temperatures were increased for various operating conditions from 35 to 45 degrees. The thrust of the objective engine was really way up there for this period of time when we looked at a 35,000 pound thrust engine. The Air Force in November of 1960 issued their Advanced Development Objective number 20. And the immediate objective was to achieve nuclear flight in a military prototype aircraft at subsonic performance levels matching the Department of Defense guidance. The initial system would have been used to evaluate the practicality of subsonic nuclear missions of long endurance, such as air alert, missile launching, low-level penetration, logistics, reconnaissance, air early warning, anti-submarine warfare, and airborne command posts. The subsonic system would also serve to develop a basic equipment and operational technology leading toward supersonic nuclear aircraft capability. As a result of this advanced development objective, a number of application studies were made for installation of the XNJ-140 power plant in the Convair Model 54, the NX2 version. Both 3 and 4 engine configurations were studied, and all versions were designed to meet the Department of Defense guidelines. The 3-engine version is shown here, and primarily in the model, where the 3 engines are placed side by side with the air intakes in the leading edge of the wing, and 2 chemical engines mounted to assist in takeoff and in nuclear engine out operation. The differences between the 3-engine and the 4-engine configuration are shown here on this chart. Neither one of them quite made the Department of Defense requirement. While the 3-engine configuration could cruise with payload at Mach 0.8 at an altitude of 32,800 feet, and the 4-engine operation Mach 0.85 at 33,000 feet. You'll note that the rate of climb with a reactor out on a hot day is pretty pathetic. 3-engine version with payload at 130 feet per minute, and the 4-engine at 340. The ground runs were well within the limits of the runway that was proposed for Idaho Falls, which was 15,000 feet in overall length. You'll notice the rate of climb with an engine out and flaps and gear down is not bad. The aircraft gross weight is well within the limits of aircraft flying today. The 474,000 pounds for the 3-engine version and 576,000 for the 4-engine version. Also, the scheduling in response to this advanced development objective called for providing the engines for operation of this aircraft by 1965. And this schedule involved a major engineering test program, including the advanced core test, a flying test bed program, and the engineering and operational test of the NX-2. Generalized planning of the various phases of the engineering test, which would have made up the advanced core test program, were well underway in early 1961. This planning was directed toward, 1, evaluating the types, the numbers, and the location of instrumentation sensors to be used in and around the E1 engine. Secondly, establishing the design and procurement of test support equipment. And finally, 3, identifying, specifying, and actually procuring the necessary auxiliary services and systems. Detailed planning was scheduled to begin in the summer of 1961 in order to meet the 1962 ACT test date. The final, another key element in the overall XNJ-140E program was the proposed flight test of the power plant in a B-52G to be used as a flying test bed. Working with the GE Flight Test Group from Edwards Air Force Base, a program was developed to begin in 1963. The first phase of this program was to be conducted with a chemically powered version of the power plant. The second phase would call for one single nuclear power plant mounted on one side of the aircraft, with a final phase consisting of the aircraft carrying 2 XNJ-140 engines. The B-52G performance could have been capable of full nuclear flight while carrying the 2 power plants and the 8 J-57 engines. This recommendation, as well as the entire A&P program, was terminated following the President's annual budget message to Congress on March 28, 1961. The program termination was based on the fact that there was not considered to be a specific military requirement for a manned aircraft with the characteristics of the subsonic long-endurance mission that was under development. At the time of termination, the XNJ-140E program was on schedule. The basic turbo machinery had been operated on chemical heat sources for a total of 758 hours using several different engine buildups. Structural modifications were in process to adapt the turbo machinery to the specific configuration of the power plant. Design of the reactor shield assembly and subassemblies had been completed. Manufacturing drawings of the parts had been completed or were in progress. Prototypes of the critical components had been proof tested. Beryllium oxide fuel tube assemblies for use in the reactor had been tested for a total of over 10,000 hours in the materials test reactor, the Oak Ridge research reactor, and as inserts in the Heat Transfer Reactor Experiment test vehicles. Reactor critical experiments had verified the fuel element loading specifications. Permission had been requested to proceed with manufacture and assembly of the reactor and propulsion machinery. Ground test schedules, as mentioned before, were scheduled for 1962, flying test beds for 1963, and NX-2 operations for 1965. Overall, the development effort expended on the XNJ-140E in the short period from mid-1959 to the termination in March 1961 produced remarkable results. Developments in the design of high-temperature nuclear fuel elements, in lightweight shielding, in nuclear reactor engineering and design, and in the accommodation of the crew in a manned nuclear aircraft for long periods of time, and further in the design of facilities. These push technologies to new limits, and I think that all who participated in this program could and should be very proud of the many accomplishments of the effort.
I'm holding here a model of the Russian or Soviet nuclear aircraft at some artist's conception. Now this was probably made about 1964, somewhere around that.
Probably earlier than that. I think it was probably around 1957 or 58, that early. And it was presumed that the Russians were building such an airplane. Turned out later that they were not.
It was not true, right?
There was a textbook written in Russian, which a number of us got copies of there at GEA&P.
This is probably an Aviation Week at the time.
Aviation Week.
Yep.
And then a local model company made models and sold them at the 5 and 10 cent store.
Yeah. Aurora, they made a lot of models.
Some comments follow regarding the Soviet aircraft Nuclear Propulsion Program. About 1956, a Russian research paper was forwarded from Washington, D.C. It mentioned both zirconium hydride and yttrium hydride. This came as a surprise. Both moderators were handled at A&P as secret restricted data. A breach in security, possibly at a vendor, was suspected. FBI and others looked into it. We never found out anymore. Later, a Russian paper mentioned their success with barylides. A&P laboratories thoroughly investigated but found nothing useful. The paper was probably planted by the Russians to mislead us. In an effort to understand the Russian literature, in the spring of 1958, after hours course in scientific Russian was offered at A&P. Nathan Gilbert, of Russian descent and a professor of engineering at the University of Cincinnati, kept the course hopping. Howard Eagle remembers that Fritz Metzger, with his physics background, was the star in the class. Others were John Moteff, Fred White, Miles Leverett, and probably Bob Van Houten and Austin Corbin. Later, in 1958, Aviation Week, the respected technical magazine, broke the news that the Soviets had flight tested a nuclear-powered bomber. In his editorial, Lou Holt said, "The Soviets have needlessly beaten us to a significant technical punch." U.S. Defense Secretary McElroy was highly skeptical. President Eisenhower said there was no reliable evidence of any kind, and he was not changing the A&P program to achieve early flight. After the Cold War, in the early 90s, U.S. intelligence agents visited Russian facilities and spoke to knowledgeable Russian engineers about the A&P program. Their conclusion was the Russians did not build an atomic-powered plane.
In 1953 or thereabouts, there was a big study of advanced different types of reactors with potential application to the nuclear-powered aircraft. And the advanced design group headed up by Ed Schmidt at the time, working for Miles Leverett. Various people studied different concepts. I started working on a concept for a ceramic reactor and studied the possibility of such things as beryllium oxide, zirconium oxide, and silicon dioxide, and concluded that a reactor possibly out of beryllium oxide was feasible. This is working in close conjunction with Vince Calkins and Clay Brassfield. Clay then developed a technique for extruding beryllium oxide fuel elements and mixing the uranium dioxide in the beryllium oxide in, as he told me, a solid solution, and perfected the technique of producing such a fuel element. In the meantime, application studies were continuing, and it was concluded by me and some other people at least that a nuclear-powered ramjet was a logical application for nuclear power, although the A&P department was at that time dedicated to the turbojet application in the manned aircraft. The Air Force then initiated a series of studies, contracted with Chancellor Aircraft, North American Aviation, and Convair San Diego to study the feasibility of a nuclear ramjet. Chancellor had the winning solution to the ramjet, and this is a model of the SLAM missile that was developed at the time, and a road carrier to play the shell game on the western part of the United States with a nuclear-powered missile, with the ramjet inlet, the boosters, and the ceramic reactor for the propulsion. Avionics was in the front end of the missile. This missile was about 90 feet long and some 5 feet in diameter, and was designed to fly at Mach 3 at sea level, or essentially on the deck. The program lasted longer than the nuclear-powered aircraft program because it was technically considered to be feasible, but very provocative. The provocative aspect by 19 1964 caused the program to be terminated, and Chancellor Aircraft at the time, who had been taken over by Link Temple, produced a film called Muscle and Mothball, or actually a history of the SLAM program, which lasted for about 5 years. You can now see this film.
Nuclear-powered missile, which would be boosted with solid rockets to high altitude, then commenced nuclear-powered flight at Mach 3. Let down to treetop level to penetrate enemy defenses, virtually impossible to detect and intercept, and proceed to deliver successive warheads to selected hard targets with precise accuracy. The development of a suitable reactor, the last and major problem of the identified high-risk areas, continued at a rapid pace at the AEC's Lawrence Radiation Laboratory. The Tory 2C reactor was a full-scale, 54-inch diameter, flight-type reactor with a beryllium reflector. Unlike the earlier Tory 2A1, Tory 2C was controlled by rods inserted into the reactor core and driven by actuators mounted in the main air duct feeding the reactor. A new fuel element fabrication technique was used for 2C. A new fabrication plant was constructed at the Coors Porcelain Company in Colorado. The powders of beryllium oxide and uranium dioxide were first thoroughly mixed with a binder material. This plastic mass was then extruded from large extrusion presses. Drying and sintering causes a 30% shrinkage. The fuel elements are finally ground to the external hexagonal shape. Assembly of the 600,000 fuel elements, the high-temperature coated columbium base plates, the control rods and actuators into the Tory 2C reactor took place in the shops at the Lawrence Radiation Laboratory. It was then moved to the test site in Nevada. The air supply at Jackass Flats had been enlarged to supply over 1 million pounds of air, and facilities installed to preheat this air to 1,000 degrees Fahrenheit, enough capacity to simulate a 5-minute flight. In May of 1964, full power operation of this full-scale flight-type reactor took place after an initial intermediate power run. All test objectives were completely met, and conclusive feasibility was established.
All right, top round, Roy. Coming up. 420. We're on the plateau.
Exhaust air from the reactor contained less than 0.1% of the generated fission products. The thermal energy equivalent of 640,000 horsepower was unleashed on the Nevada desert. This rate of energy release could have been sustained for hours, equivalent to a missile flight around the Earth or more, had sufficient cooling air been available. Adequate thrust for the nuclear missile had been demonstrated.
All right, now